Inaugural of DAE, BRNS, INCAS National Workshop on Radiochemistry and Applications of Radioisotopes. Today is a very auspicious day as we are celebrating Vasanta Panchami and we are moving towards Radha Saptami. What a way to celebrate and what a way to start a program like this. So let us start this from a sloka from Rigveda. Urjam nodehi dvipade chatuspade Urjam Vohidnadathunha, which means, may the energy be bestowed upon us, all living organisms. May the sacred fire, Agni, provide us with this vital energy. With this, I would like to welcome our beloved Principal Sir, Chairman of this National Workshop, Dr. Ramchandra R.K. Garu, onto the dais. And I request one of our PG students to honor Sir with a sapling. Now I welcome today's chief guest, former Director of Radiochemistry and Isotope Group, Dr. P.K. Mohapatra Garu, onto the dais. And I request one of our students to honor Sir with a sapling. Thank you. Now I welcome Dr. P.S. Ramanjaneyulu Garu, convener from INCAS, onto the dais. I request one of our students to honor Sir with a sapling. And now I welcome Srimati C.H. Komalakshmi Garu, convener of local organizing committee of this national workshop, onto the dais. And I request one of the students to honor ma'am with a sapling. And now I welcome the organizing secretary and the young chap of our department, Dr. B. Gaurnaidu Garu, onto the dais. And I request one of our students to honor him with a sapling. Yeah. So now I request all the dignitaries to proceed for the lamp lighting, Jyoti Prajwalan. Now I invite Dr. A. Rajasri Garu, academic coordinator of this college, for the prayer song. Welcome, ma'am.
Thank you, sir. అంబుజవాసిని సుందరి వాణి, అంబుజవాసిని సుందరి వాణి, సరస్వతి దేవి నమోస్తుతే. అంబుజవాసిని సుందరి వాణి, పుస్తకధారిణి బుద్ధి ప్రదాయిని, పుస్తకధారిణి బుద్ధి ప్రదాయిని, వీణాపాణి త్రినయని పాహి. అంబుజవాసిని సుందరి వాణి, వేదశాస్త్రనుతే విధి ప్రియ సుభగి, వేదశాస్త్రనుతే విధి ప్రియ సుభగి, విద్యావారిధి పాహి పాహి. అంబుజవాసిని సుందరి వాణి, మాలాలంకృత మణిమయ భూషే, మాలాలంకృత మణిమయ భూషే, మందాహాసే మాం పాహి. అంబుజవాసిని సుందరి వాణి, సరస్వతి దేవి నమోస్తుతే. అంబుజవాసిని సుందరి వాణి.
Thank you, ma'am. I now welcome our beloved Vice Principal Sir, Dr. Murthy Garu, onto the dais. Now one of our students will honor Murthy Garu with a sapling. Thank you. Now I welcome Dr. Nuzila Srinivas Garu for the college song.
सरस्वती नमस्तुभ्यं वरदे कामरूपिणी, विद्यारम्भं करिष्यामि, सिद्धिर्भवतु मे सदा. जय हो मा आर्ट्स कलाशाला, जय हो मा आर्ट्स कళాశాల. భావి పౌరులకు నీవే భవ్య కార్యశాల, గౌతమి ఒడిలో విరిసిన విద్యావనమా, గౌతమి ఒడిలో విరిసిన విద్యావనమా. రాజమహేంద్రవరానికి తలమానికమా, జయ హో మా ఆర్ట్స్ కళాశాల. భావి పౌరులకు నీవే భవ్య కార్యశాల. మెట్కాఫ్ మహాశయుని ఆశయ ఫలమా, మెట్కాఫ్ మహాశయుని ఆశయ ఫలమా సార్ధశతాబ్దము నిండిన వారసత్వమా తెలుగు నేలపై వెలసిన ఘన విద్యాలయమా తెలుగు నేలపై వెలసిన ఘన విద్యాలయమా సర్వస్వతంత్రత కలిగిన జ్ఞానపీఠమా జయ హో జయ జయ హో మా ఆర్ట్స్ కళాశాల భావి పౌరులకు నీవే భవ్య కార్యశాల కూల్డ్రే కందుకూరి సర్వేపల్లి గురువులుగా దామెల్లా గాడి చెల్లటంగుటూరి శిష్యులుగా కూల్డ్రే కందుకూరి సర్వేపల్లి గురువులుగా దామెల్లా గాడి చెల్లటంగుటూరి శిష్యులుగా వెలుగులతో భాసించిన విద్యాశ్రమమా విలువలతో శోభించే దివ్యాశ్రయమా జయ హో జయ జయ హో మా ఆర్ట్స్ కళాశాల భావి పౌరులకు నీవే భవ్య కార్యశాల పాలనా దక్షులకు రాజనీతిజ్ఞులకు న్యాయకోవిదులకు నువ్వు చదువుల నెలవు పాలనా దక్షులకు రాజనీతిజ్ఞులకు న్యాయకోవిదులకు నువ్వు చదువుల నెలవు సమత మమత పండించే సస్యక్షేత్రమా సమత మమత పండించే సస్యక్షేత్రమా సమాజ దేవాలయమా పుణ్యక్షేత్రమా జయ హో జయ జయ హో మా ఆర్ట్స్ కళాశాల భావి పౌరులకు నీవే భవ్య కార్యశాల గౌతమి ఒడిలో విరిసిన విద్యావనమా రాజమహేంద్రవరానికి తలమానికమా జయ హో జయ జయ హో మా ఆర్ట్స్ కళాశాల ధన్యవాదాలు
Thank you, sir. Now, I welcome Dr. B. Gaurnaidu, Organizing Secretary of this workshop, for the introductory remarks.
Good morning to distinguished guests, Dr. P.K. Mahapatra, former Director, Radiochemistry, BRC, and also is the President of INCAS, and INCAS convener, Dr. P.S. Ramanjans Garu, and then Chairman of the this 5 days DABRN's National Workshop on Radiochemistry and Applications of Radioisotopes. Sir, beloved Principal Sir, Dr. Ramchandra R.K., and then our beloved Vice Principal Sir, Murthy Sir, and then our Head of the Department and local convener of this 5 days workshop, Srimati C.H. Komalalakshmi Madam Garu, and scientific officers from BRC, and then heads of the departments of science and arts from GCRGY, and all the faculty fraternity, and all the dear participants. So, warm welcome and good morning to all. So, So this workshop comes at crucial time in evolution of nuclear science and technology. So where our understanding of radiochemistry and radioisotopes continues to expand the horizons of research and innovation. So our collective journey in this field is driven by the passion for scientific discovery and commitment to apply the knowledge for the benefit of the society. Today we gather not only to share our research findings and technological advancement, but also to foster new collaborations and inspire fresh ideas and reinforce our shared vision for a future where nuclear science plays a pivotal role in addressing real-world challenges. Over the next few days, we have carefully curated the program that features a series of technical sessions, keynote lectures, and hands-on experiments. These sessions are designed to encourage in-depth discussions and critical analysis of the last developments in radiochemistry, from the novel radioisotope production techniques to innovative applications in medicine, industry, environmental science, and research and development. We are especially proud to bring together a different group of experts and young researchers and students whose contributions are critical to the progress of our field. So I would like to express our sincere gratitude to the Department of Atomic Energy, Board of Research in Nuclear Science, and Indian Association of Nuclear Chemists and Allied Sciences for their visionary leadership and unwavering support. Their commitment to advanced nuclear research has been instrumental in making this workshop possible. We are also grateful to our sponsors, organizing committee, and all the staff who have worked tirelessly behind the scheme to ensure the success of this event. The theme of this workshop, entitled Radiochemistry and Applications of Radioisotopes, reflects the dual nature of our work, delving into the fundamental chemistry of radioactive substances while simultaneously exploring the practical applications that improve human lives. Whether it is medical diagnostics and therapy, industrial radiography, environmental tracing, or the development of new materials, radioisotopes serves as indispensable tools that bring the theoretical research and real-world application. This workshop is an ideal platform for us to delve into the topics, share experience, and chart out pathways for the future research collaborations. I encourage each one of you to actively participate in the discussions, ask probing questions, and share your insights. Let us use this opportunity to build lasting connections and to inspire one another with the collective wisdom and innovative spirit that defines our community. Your contributions, whether in the form of groundbreaking research, insightful critiques, or novel ideas, are the essence of this workshop and will undoubtedly shape the future of radiochemistry and its applications. In closing, I extend my heartfelt thanks to all of you for being here today. Your presence reinforces the importance of work and inspires us to push the boundaries of science further. Let us embark these next few days with the curiosity, determination, and shared goal of advancing our understanding and applications of radioisotopes for a better tomorrow. Thank you, and I wish you all a productive and inspiring workshop. Thank you all.
Thank you, Dr. Gaurnad Garu, for his interesting introductory remarks. Now, I heartfully welcome our Honorable Principal Sir, Dr. Ramchandra R.K. Garu, Chairman of this workshop, for the welcome address. Sir.
A very good morning, ladies and gentlemen, and today's esteemed guests, Dr. P.K. Mahapatra, outstanding scientist from and also Director Radiochemistry and Isotope Group, Head Radiochemistry Group, Baba Atomic Research Center, Department of Atomic Energy, Government of India, and also another esteemed guest on the stage, Dr. P.S. Ramanjanayal Garu, Head High Temperature Analysis Section, Radio Analytical Chemistry Division, Baba Atomic Research Center, Mumbai, and my Vice Principal, Shri Ramurthy Garu, and also a 5 days workshop convener, Dr. Komal Lakshmi Madam, Head Department of Physics, Government College, Rajahmundry, and also Organizing Secretary and leading this workshop, Dr. Gauri Naidu, Department of Physics, and other scientific officers from Baba Atomic Research Center, Mumbai, and head of the departments of Science and Arts and Commerce, and students, research scholars, press, print and electronic medium. So a very good morning to you once again. And also it's my pleasure to welcome you on behalf of 172 years Government College Autonomous Nake Place, Rajahmundry, Andhra Pradesh. And so it is a very good workshop on radiochemistry and applications of radioisotopes. And my special thanks to INCOS, Indian Association for Nuclear Chemists and Allied Scientists group from BAC. And this is a second of its kind to organize this kind of workshop. The first, it was taken place in the year 2014 and 15 by the Department of Chemistry. The same workshop has been conducted by the college. And this is the second time. Now it's turned to physicists and physics department, and especially a nuclear physicist is Gauri Naidu, and myself also nuclear physicist. We had a thought to conduct this workshop. Immediately, INCUS responded well and obliged our request, and finally it is realizing for the coming 5 days. And as you know all, the radioisotope is nothing but an atom which contains unstable neutrons and protons in their nuclei, and which leads to the radioactivity, and it harnessed n number of numerous applications in industry, medicine, and as well as scientific research. So this workshop is not just theoretical classes, and it's hands-on experience. They have a meticulous program for the coming 5 days, and they are going to organize some practicals on different nuclear instrumentations. And they bought instrumentation and the respective radioisotopes from BARC. And really, suppose whatever we have read in the textbooks and whatever we have knowledge, theoretical knowledge, once you feel that exposure with a practical way, then definitely it has its own impact. And nowadays, radioisotopes applications are in almost all the fields. In case of medical field, detecting tumors, and then cancer applications. So one of the deadly diseases faced by the human beings. So we can at least stop somewhat to spread over the body. The nuclear radioisotopes gives a best attention towards attention by the doctors to save the patients from deadly diseases, cancer. And also industrial applications is also there for sterilizing and to increase the sustainability of some kind of groceries and all. And scientific research anyway to understand the basic nuclear physics laws. And these are n number of applications are there. A series of lectures has been arranged for the 5 days, and also a lineup of scientists are there. Nearly 6 scientists are going to enlighten you on this particular radioisotopes and their applications. And definitely this particular workshop provides a platform to share each other their expertise. And I wish this particular workshop is going to be a great success, and also it has a productive outcome definitely at the end. And the participants who came across the nation, and I wish you a very pleasant stay for the coming 5 days. And the organizers, a special thanks goes to organizers and the Department of Physics for arranging nice workshop. And this workshop definitely, so initially we thought it in 1 or 2 or 3 days, but it's a 5 days means it's also helpful for career advancement schemes and all. So that is a one kind of thing. And this particular workshop has been recognized by Commissionerate of Collegiate Education, our director, and given OD, those who are participating lecturers across the state, definitely they'll utilize this opportunity. And once again, I thank the DAE BRNS INCOS for arranging nice workshop and take pains to come all over from Mumbai to here and organizing this workshop. So I wish you very all the best. Thank you.
Thank you, sir. Now I welcome Dr. P.S. Ramanjaneyulu garu for the inaugural address.
Dignitaries on the dais, Dr. P.K. Mohapatra, Dr. R.K. Ramachandra, Dr. B. Gaura Naidu, and Sri Mati Lakshmi Garu and Murthy Garu. A very good morning to all of you. And it is my honor and privilege to welcome you all for the DAE BRNS, that is Department of Atomic Energy and Board of Research in Nuclear Sciences, 109th INCOS workshop on radiochemistry and application of radioisotopes. For you maybe all are agree with me that whenever we are starting anything new experiment or anything proposing any plan for the any project, we'll always say that what is the aim of your experiment. I mean, you want to say that what is the aim of this experiment or what is our plan of project. The same way, for conducting this workshop also, we have the two aims, not one. The first one is the popularizing the nuclear sciences among all the academic institutes. For this purpose, we are targeting the faculty members, research scholars, and postgraduate students, such that they will choose as the one of the important branch of sciences, that is the nuclear science and allied sciences, as they is their career opportunities. And second one is the popularize the DE, nuclear energy and its applications to the public to enhance the popularity. And for this purpose, we are selecting your faculty members and all research scholars and students, such that we hope that after the end of this workshop, you all become like a brand ambassadors for the DAE, such that you will spread this awareness of applications of nuclear energy into the masses. And this is the aim. And the curriculum of our workshop consists of with the simple fundamentals of radioactivity and their applications. And it is a present workshop. We have the 2 keynote lectures and 12 lectures will be delivered in the forenoon session among these all 5 days. In the afternoon sessions, we will conduct the hands-on experiments where we will demonstrate what the practical applications of radioactivity and how they will measure. It is simple experiments such that we will get the hands-off experiments feeling. In the first keynote lecture will be delivered by Dr. P.K. Mohapatra, where he will discuss about the DAE at glance, that is the atoms in the service of the nation, and he will give the lectures on what the different activities we are doing in the DAE and its societal applications. And the second keynote lecture will be delivered by Dr. Y.K. Bharadwaj, as Associate Director of RC and IG, where why the radiation is so versatile and what is the application for societal benefits. And remaining the lectures will be consist like the fundamentals of radioactivity, and then the nuclear structure and stability, and its nuclear fission, and its the interaction of radiation with matter and its application for their measurement. And some of the lectures also dedicated what is the peaceful applications of nuclear energy, so like nuclear reactors, the production of radioisotopes, and its application in healthcare, food, agriculture, and industry. And also you all agree that the nuclear analytical techniques is one of the fundamental tool in any research, because it can solve the variety of problems whatever we are facing in our scientific career. Now the one lecture will be delivered on the application of nuclear analytical techniques in the research. And also as per the Prime Minister of India Dr. PM Modi is, as per his call, that India should become the Viksit Bharat by 2047, and then this is only possible if you create the wealth that it requires the needs of all the population of India, and that is only possible with only the science and application, science and technology. Now, for this purpose, we want to see that in addition to the nuclear energy generation, the DE also develops so many technologies. Now we want to say that this technology should go to the masses. For this purpose, we are interacting what the DE technologies. We wanted to interact with some entrepreneurs. Maybe some of them, maybe people are maybe in the future, maybe they will become entrepreneurs. At that time, maybe they consider what are the DE technologies that they can suit. They can select this one of the technology as their option. The one lecture will be delivered on the DE technologies and its societal benefits. And also, any institute they prosper with the induction of the new and efficient manpower. And for this purpose, we are giving one lecture on what are the career opportunities in the DAE. Now, one of the important part of this workshop is we are conducting the experiments, that is the hands-on experiments, where we will demonstrate what is the fundamentals of radioactivity, how it will be measured, and what is its application in the research. Then the afternoon session, we will conducting every day the practicals, and then I invite you all to actively participate in this workshop and doing these experiments. And then each day we will conduct the work quiz program after the end of our technical lectures, and then the people who are given the answer will be awarded for that. Yes. Okay. Before concluding my inaugural address, I just want to mention the INCAS, the Indian Association of Nuclear Chemists and Allied Scientists. It is very strong bonding with you all the people, because there is the founder president, Dr. M.V. Ramanaya. He is born in our East Godavari district, and he did his masters from Andhra University, and then he has done the postdoctoral degree with the T.C. Burr, who discovered the plutonium, and later they are able to extend the periodic table. Now we have a very strong bonding with your East Godavari district people for the INCAS. I hope there may be so many Ramanayas are maybe sitting in this auditorium. Maybe at present may not be choosing what is the nuclear science. In the future, maybe they will select this nuclear science as one of the career opportunities, and maybe our DE will also prosper with the induction of so many Ramanayas in this auditorium. Okay. On this auspicious day, the Vasanta Panchami, where the kids will start the Aksharabhyasam, and we also hope that the new interaction, will start the new interaction with you all the people, and INCAS and our Government Arts College. With this, I will conclude my inaugural address. I welcome you all for once again the 109 INCAS National Workshop on Radiochemistry and Application of Isotopes. Thank you all.
Thank you, sir, for a very interesting address and also encouraging the students to start studying nuclear physics. Now I welcome today's chief guest, Dr. P.K. Mohapatra Garu, for addressing the audience.
Dr. Ramchandra, the principal of this college, Dr. Murthy, the vice principal of the college, Dr. Komala Lakshmi madam, Dr. Ramananjalu, my colleague from BARC, Dr. Gauri Naidu, faculties of this college, delegates, students, ladies and gentlemen. A very good morning to all of you. Initially, I want to start with this nuclear science. There is a very bad memory of this nuclear science. When anybody talks about nuclear science, you start remembering this unfortunate incident in 1945 that stopped the World War II. And when you talk to anybody in the villages about the nuclear science, they think that it is nuclear weapon, which is not correct. When Dr. Homi Bhabha started the activities, the nuclear science in BARC, and subsequently it was initially, of course, it was not called BRC, it was called Atomic Energy Establishment, or AEE. And then subsequently, we started the Department of Atomic Energy in 1954. So the major focus area was to generate the power. So Dr. Bhabha was having the foresight that there will be energy crisis because of the increasing population and the developments taking place all around the world. So the major application will be the production of power through nuclear reactors. And second application is the isotopes, which will be used for mostly for cancer drugs and also diagnostics. So for that, the first nuclear reactor was started in the Trombay campus of BARC, or the Cyrus reactor in 1960, which was decommissioned, of course, after 50 years in 2010. So all these activities was started by late Dr. Homi Jahangir Bhabha, and this was the major application of nuclear science, whether it's nuclear physics, whether it is radiochemistry. This was the major applications which was envisaged at that time by Dr. Bhabha, and we have carried out this all along, over this past so many years, 70 years or so. And as Dr. Ramanjalu was telling this, late Dr. Ramaniya, who was our director of this radiochemistry isotope group, radiochemistry group that time, and he had the vision, this popularizing nuclear science. When the people start, people have this negative opinion about nuclear science, so it was very relevant to start the outreach to the masses about the benefits of nuclear science, how this power production or the isotope application. So he started this YANCAS in 1981. So it is now more than 45 years. This has been started, more than 40 years, in fact, it has been started. And subsequently, Dr. Ramaniya started another scientific body called the Indian Nuclear Society. That is a much bigger body than the YANCAS. But YANCAS has the role of popularizing science, mostly, though the name suggests that it is a nuclear chemist and allied scientist, but there are a lot of nuclear physics people are member of this YANCAS, because there is no distinction between nuclear chemistry and nuclear physics when you carry out top level research. And YANCAS has been very methodically working, as already you know that it is a 109th workshop. So many places YANCAS has been organizing workshops, I think around 2 to 3 workshops every year, sometimes even more than 3. And so we are trying to popularize nuclear science, but I think this part of Andhra, YANCAS, this nuclear science was already existing when the YANCAS was formed. I think Professor M.N. Sastry from Andhra University, he is a very reputed nuclear scientist. Along with Dr. Ramaniya, Professor Sastry, Professor B.M. Sukla, and all these people, and Professor Arnikar from Pune, they all founded this YANCAS activities in the early 1980s. And that is how actually we are spreading awareness amongst our different research institutes, colleges, and then where students are giving these lectures. What are the real benefits of the nuclear science? And through these nuclear reactors, of course, there are facilities which are available. These are the facilities of the nation, where not only the nuclear physics, even solid state physics people can carry out a lot of structural studies using the reactor beams. So I think this is a great opportunity where we'll be really opening up what are the positives of this nuclear science, whether it is radiochemistry research, nuclear physics research, or even this isotope application. There will be lectures, as Dr. Ramanjalu mentioned, there will be different lectures, and also there will be practical, there will be 4 practicals will be there, which will really popularize the nuclear science to the students, the participants of this workshop. This coming to YANCAS, YANCAS has been having different activities broadly, we are organizing a biennial symposium called the Nuclear and Radiochemistry Symposium, that is NUCAR. This year it is there, in fact, 25 April it is there. And those of you carrying out research in these areas, you can now submit, I think the window is open for submission of papers for presentation NUCAR 25. And this is one of the very major activities of YANCAS through NUCAR. And we have another activity is conducting these workshops, which you know that this workshop is also being now done under 109th workshop. Then there is a third activity of NUCAR, YANCAS, is the publication of bulletins. So very popular bulletins are published every year. I think around 3 to 4 bulletins are published every year on topics relevant to Department of Atomic Energy or nuclear science. So those are also through YANCAS, you can avail the facility of these bulletins. There are many members of YANCAS, I think several thousands members are there now. Now those of you want to become a member, then you get some special privileges by getting the facilities offered by YANCAS through the facilities of Department of Atomic Energy through YANCAS. So you can always contact the local convener, Dr. Gauri Naidu, if you want to avail these facilities. And of course, you can interact with our resource persons, and they will be fully available during the period of this workshop to respond to your queries about nuclear science, YANCAS, all this. And how to, another of course objective is how to carry out nuclear research, because we are seeing over this past several years, there was a conscious decision by some of the Western countries to shun the nuclear power. They were thinking that we should go green, so there will be no nuclear power in some of the countries like Switzerland, Germany, Belgium. They were not having this nuclear energy. In fact, the reactors started shutting down there. I think around 2000 or so. Mostly these green parties are coming to power there, and they are against nuclear energy. But because of this recent develops in Europe, that is the Russia-Ukraine war, the petrol prices has gone up, and you have seen that now people are coming back to this nuclear power. The focus has shifted to nuclear energy once again. And also this Paris Agreement, which says that net zero, this carbon dioxide emission should be completely made zero. So for that matter, this nuclear energy again come to limelight. And you will see that nuclear energy, even though these green parties were opposing this nuclear energy, thinking about the nuclear waste, I think in the course of this YANCAS workshop, you will find out that these wastes are much, much less coming from the nuclear energy as compared to the other energy. In fact, the accidents are very, very less in the nuclear energy. There are hardly, some 3 accidents, major accidents, you can say, like in the nuclear energy over the last nearly 70, 75 years of operation. So I think it's a very good incentive to opt for nuclear energy, particularly with the net zero targets. India has a target of 2070 as the net zero target. So our efforts are also will be there to have this nuclear energy. Finally, I want to mention that our YANCAS program has been supported by BRNS, even though our human resource is given by our BRC, but the money comes from BRNS. So we thank BRNS for supporting our YANCAS program. And finally, I welcome all of you for this 109th YANCAS workshop, and please ask whatever questions you have in your mind to all our resource persons, and so that you get completely clear knowledge about this nuclear energy and nuclear power. So thank you very much.
Thank you, sir, for clearly explaining the positive sides of nuclear science and the nuclear energy, and also explaining about YANCAS objectives and its history. Now I welcome Srimati C.H. Kamalakshmi Garu for her remarks.
Good morning, one and all. Respected Principal of this college, Professor Ramchandra R.K., and the chief guest of this occasion, Dr. P.K. Mahapatra Garu, Senior Scientist and former Director of Radiochemistry and Isotope Group, Mumbai, and Dr. P.S. Ramanjanelu, Head and High Temperature Analysis Section, BARC, Mumbai, and Vice Principal of this college, Dr. Sriramurthy Garu, and the Organizing Secretary, Dr. B. Gauri Naidu, and all the scientific officers and the delegates on the dais, of the dais, and my dear colleagues, staff, students, and participants, a warm welcome to these national workshops of our 5 days on radiochemistry and application of radioisotopes. Our institution, that is the Government College Rajahmundry, being 172 years old, serving nearly 7,000 students, and it is one of the premier government educational institution in the state. And the Department of Physics was established in this college in 1930. In this 95 years of long journey of the department has given many star awards to the society across the globe. And at present, our department consisting of 24 faculty as teaching and 7 non-teaching staff work as a team under the for the student benefit community under the leadership of our principal, Dr. Ramchandra Garu. And with the implementation of this NEP 2020, our department offers 4 major streams, namely physics honors with research and electronics, material science and renewable energy management with an intake capacity of 180 students every year, and also 1 pre-Z program, MSc Physics, with an intake capacity of 36 students. Basically, organizing this workshop in association with BARC and INCAS Mumbai is a great opportunity of this department. In this regard, I extend my thanks to all the resource persons for giving us opportunity. Our aim in this institution for conducting this workshop is to explore for diverse uses of radioactive isotopes in various fields, showcase real-world examples of radioisotopes applications, and provide hands-on experience on radioisotopes related experiments. I am sure that this workshop brings in new skills, insights, and valuable inputs to the participants and help them to apply them practically. Moreover, it creates enthusiasm towards the subject learning. Hence, every participant make use of this great opportunity so that this purpose has been fulfilled. Thank you. Thank you very much.
Thank you, ma'am. Now, before closing this inauguration, let us thank all the people who helped for successfully organizing this inauguration, and let us start with our beloved principal sir, who supported us throughout, both in leadership and financially, for conducting this workshop. And I thank our sponsors who sponsored for this workshop. And also, I would like to thank today's chief guest, Dr. Mahapatra Garu, for his very valuable and insightful remarks. And I thank Ramanjanelu Garu for clearly explaining the motto of this workshop. And I thank HOD of Physics Department, Srimati Kamal Lakshmi Garu, for explaining about the Physics Department of this college and also how this workshop is going to help the student fraternity and different participants in this workshop. And I would like to thank Dr. B. Gauri Naidu Garu, who spent sleepless nights. I think last 1 week he didn't sleep much for conducting this workshop. So this is really great because he's such a young guy, but he's taking a lot of pain for conducting this. Thank you, sir. And I thank Vice Principal Garu for his constant support. And I thank all the non-teaching from Physics Department who are helping continuously for conducting this workshop. I also would like to thank all the coordinates of different parts of our college and all the HODs of the department and all the students and media people who are part of this workshop for the successful inauguration. And I would like to say one Sanskrit a phrase which is also slogan for our college. Yadho dharma stutho jayaha. That is the slogan of our college. So where there is dharma, there will be victory. So in nuclear physics, I think this is highly applicable because the right way of using nuclear science is generating energy and using it for different applications of medicine, agriculture and others. Not in war, not in bombs. That's why it is the dharma that decides the victory. It is not the weapons that decides the victory. Thank you. Now we'll have high tea. So I request all of you go and have high tea. Then we can start our workshop. Thank you. Half
Yeah.
Welcome back. So today we are going to start the first session of this workshop by Dr. Mohapatra Garu on DAE at glance, peaceful usage of atomic energy. Now I request Dr. Yusubhasha Garu to introduce Dr. Mohapatra Garu.
Good morning, dear participants. I feel much privileged to introduce Dr. P.K. Mohapatra, outstanding scientist, former director, Radiochemistry and Isotope Group, and head Radiochemistry Division, Baba Atomic Research Center, Mumbai. Sir did his MSc from Utkal University, Bhubaneswar in 1985, and then after graduating from 30th batch of BARC Training School, Sir joined in Radiochemistry Division BARC in 1987. Sir did his PhD from University of Bombay in 1994 and did his PhD work on studies on the complexation of actinoids with some microcyclic ligands. Sir has did his postdoctoral research at University of Liege, Belgium under Boyce Cast Fellowship and DST on MRI contrast agents, and he also did another PDF from University of Mainz, Germany on the chemistry of super heavy elements under the Alexander von Humboldt Fellowship. He has been awarded the DAE SRC Outstanding Research Project and Homi Bhabha Science and Technology Award of the Department of Atomic Energy. Sir is a fellow of National Agency of Sciences and Royal Society of Chemistry. And Sir is listed among the top 2% of scientists and engineers in chemistry and chemical engineering by a study done by Stanford University of Scientists. It's really great news. Sir's research interests include separation of actinides and fission products using novel extracts, novel separation techniques in molecular diluents, which is ionic liquid-based solvents. Sir has worked extensively on the separation techniques including liquid membranes, hollow fibers, phase inversion beads, etc. Sir is also an expert in the actinide chemistry with special emphasis on the solution chemistry of actinoids. Sir has developed a hollow fiber liquid membrane separation method for the recovery of actinides and fission products from radioactive waste samples. Sir has several national and international collaborations such as University of Twente, the Netherlands, Lomonosov Moscow State University, Russia. Sir has supervised several PhD students from DAE and other allied institutes. Sir served as a training school teacher for actinide chemistry course and later coordinator for actinide chemistry course. Sir is currently the current chairman of Board of Studies of HBNA for Chemical Sciences. Sir has also delivered lecture on actinide chemistry on the NPTEL platform on the chemistry of actinides in nuclear and radiochemistry course. Presently, Sir is heading radiochemistry division of BARC and is a director of radiochemistry and former director of radiochemistry and isotope group BARC. He has over 440 papers in peer-reviewed international journals with over 10,000 citations. He has delivered over 60 lectures in conferences or symposia. He has served as the associate editor of Royal Society Chemistry Advances and currently is the editor of Radio Chemica Acta and associate editor of Separation Science and Technology, which are the reputed international journals in the areas of radiochemistry and separation science, separation science. With this brief introduction, I welcome Dr. P.K. Mahapatra sir to deliver his lecture. Sir, our participants are degree college physics faculty and research scholars from various national universities and MSc physics students and BSc physics students, sir. Welcome, sir.
Thank you for your introduction. So in the inaugural session, I mentioned about this, gave a glimpse of this DAE activities. Now I will go a little more detail about the DAE activity at a glance. And this is mostly, as I mentioned, is the peaceful uses of atomic energy. So this is the outline of my lecture. There is a nuclear power production, isotopes for societal applications, under which there will be, just briefly I will mention about radiopharmaceutical diagnosis and therapy. Subsequently, Dr. Tapas Das, who is the head of radiopharmaceutical division, he will give a detailed lecture on this radiopharmaceutical diagnosis as well as therapy. I will also touch upon this industrial application and isotope hydrology, which will be, I think, Dr. Atanu Jha, I think there will be a lecture separately for this. Then radiation for societal applications, this radiation processing of food, nuclear agriculture. I don't know whether there is any special lecture for this, these two things, agriculture as well as processing of food. Then radiation for treatment of this sludge hygienization as well as the wastewater treatment that Dr. Atanu will be presenting. So these are the brief outlines of the lectures. Now coming to nuclear power. So actually worldwide this is a global scenario. I think updated at the end of 2023. So there are 422 reactors and around 31 years is the average age of these reactors, and it is the total share of this nuclear energy compared to the all others. This is, you have this only 6% for the nuclear energy, renewables 23, fossil fuels are still 71%. So when you talk about the net zero, these fossil fuels should go to zero. And then of course the solar and you can see here this is a share of nuclear energy in global electricity production. So there was a peak actually in 1996 when this nuclear was having a maximum share. Subsequently, because of the other things are increasing, so then mostly the renewables, so then nuclear is now steady around maybe 10% or so for the last several years. Now coming to our nuclear power in India, as of November 24, India has 24 nuclear reactors in 8 nuclear plants, and we have this now 8180 megawatt electrical is the installed capacity. We have 11 more reactors which are under construction with a combined generation of 8700 megawatt electrical. These actually there was a more or less plateau in this nuclear capacity for quite some time, but I think last year there was some increases there, that it has come from 6700 to 8180, and there will be, I think, next few years it will be another 8700 megawatt electrical will be added. So there will be a big jump in the nuclear power production in India. Their factors are different, which I think in the course of this workshop you will be knowing what are the factors why this nuclear energy was at a standstill in India, and now there is a big boost. So these are the other countries. This particularly United States with the nuclear is nearly 20%, and France you have nearly 62% is the nuclear, the total energy production. So India also will be catching up slowly with this increase in the nuclear energy as the more number of reactors are coming up. So this is just gives a total for India is the installed generation capacity. You get nearly total fossil fuel is 56.4%, and total non-fossil fuel is 43.6%, and out of this nuclear is only 1.8% when this total installed capacity from nuclear was 7480. So now it is just above, I think, 2%. So this nuclear, because of this recent addition in the reactor capacity. Now this is a brief schematic how this nuclear energy is being generated. So Homi Bhabha, he has envisaged this nuclear power in the 3 stages of this nuclear energy programs. So the first stage, which most of you must be knowing, I think this nuclear physics course, I think this is a physics department. I hope that this nuclear physics introduction will be taught to you. And for the other delegates, those who are aware of this principle of this nuclear energy, you know that this nuclear fission is the main source of this nuclear power, nuclear energy. This is because when you start having natural uranium, either you have the natural uranium or you have the enriched uranium. In most of these other countries, they are going for this enriched uranium as the fuel, where uranium, as you know, it has 238 uranium as the major constituent, nearly 99.3%, and around 0.7% is the uranium 235. So which is the fissile content of this uranium in the fuel, and that undergoes fission, And as it is shown here, if it is uranium-238, it cannot undergo fission, so it captures a neutron and to give activated uranium-239, which is short half-life, it decays to neptunium-239. This also has a very short half-life and it decays to 239 plutonium. This is again a fissile material, and then this is going to the second stage of the nuclear energy program as envisaged by Dr. Bhabha. So there you have this plutonium as the fissile, plutonium-239 as the fissile material, and you have a thorium blanket where thorium-232 is getting again neutron activated to 233 uranium, and that ultimately giving 233 uranium, which is again fissile material. So this third stage of the nuclear energy program will be based on the uranium-233. So there are three fissile actinide radionuclides which are actually useful for these three stages of nuclear energy program. First one is uranium-235 which is naturally available. So that is used in the first stage of the nuclear energy program. We have this pressurized heavy water reactors where you use natural uranium as the fuel. So 235 uranium is used in this case for as the fissile isotope. The second stage we have the fast breeder reactors. So there we have the plutonium-239 as the fuel, and the third stage we have this fissile 233 uranium that is used as the fissile material in the third stage of the nuclear reactor. I give some of this. This is a very recently which has gone critical, is the Kudankulam nuclear power project. Now coming to this fission reaction, as I mentioned, uranium-235 is the fissile nuclide and takes up one neutron. This is actually a thermal neutron which is takes up. I think details will be there in some subsequent lectures, it will be there why it is a thermal neutron is used and not the fast neutron. We will be taught about the neutron spectrum in a reactor, how the neutron energy is there in the different energy neutrons are available in the nuclear reactor. And a thermal neutron with an energy of 0.025 electron volt will be bombarding with the uranium-235 to give two fragments, fission fragments, and around 2 to 3 neutrons and 200 MeV of energy which is coming out of this. So this bottom line is that you have 200 MeV of energy available per 235 radionuclide fission, and this is all of this is available as the heat, and then which is capitalized in a nuclear reactor, and that energy is given to you as nuclear energy. Now you know that this fossil fuel has been mostly in India. We have a lot of these thermal power plants, that is coal is the major constituent fuel. So we just give a comparison of 235 uranium fission versus the fossil fuels. So how many kgs of coal are required to provide the energy in 1 kg of natural uranium? So for this number of atoms, this 235 in 1 kg of 235 in 1 kg is natural uranium contains 0.72% of 235, and 1 kg of natural uranium contains 0.0072 kg, and if you see the number of atoms, you multiply with the Avogadro number and you will see the fissile content, and then you find that total is the 1.845 10 to the power 22 atoms. Now total energy released is this, you multiply with this 200 MeV, and finally you find out this much joules, that is 5.9 10 to the power 11 joules. Therefore the specific energy of natural uranium is 5.9 10 to the power 11 joules per kg of this, because we started with 1 kg per kg of this uranium. Now specific energy of coal is 2.37 10 to the power 7 joules per kg. So the amount of coal needed to release same amount of heat is 5.9 10 to the power, that is 5.9 10 to the power 11 joules is 25 metric tons of coal. So that is a huge amount of coal compared to only 1 kg of uranium. Now coming to the calorific value of fossil fuels, this domestic coal is around 4,000, imported coal is 5,400, naphtha 10,500 and LNG 9,500. This Indian uranium ore contains only 0.06% of uranium because we are having very poor quality ore, whereas Canada has got a much better quality ore with 18%. This provides 20 times more energy per ton of the mined material than coal when uranium is used in a once through open cycle in PSWR. Now, as will be mentioned in one of the lectures, how this uranium can be recycled. We have a closed cycle program. This is an open cycle mostly in countries like United States of America. They have this fuel in something called the open cycle. They use only once, and then after the reactor this is not used any further. Wherein in countries like India, where you have a poor source of uranium, poor availability of uranium, so we go for the closed fuel cycle where this spent nuclear fuel is reprocessed in a plant and then it is again used in the fabrication of the fuel. So 1200 to 1400 times more energy per ton of the mined material than coal when used in the closed fuel cycle based on the fast breeder reactors. Then this 1000 megawatt electrical nuclear power plant needs movement of 12 trucks, that means 10 trucks, 10 ton per truck of the uranium fuel per year. Please note this is per year. We need only 12 trucks of uranium, whereas for a 1000 megawatt electrical coal power plant needs movement of 3,80,000 trucks of coal per year. So this is a huge difference when you see the inventory of uranium as well as coal. Now, of course, we have large deposits of coal in India, but now coming to the resources, you see the coal left as per this is again I think 2-3 years old data I am presenting here. The United States was having 470 years and India is having only 111 years of coal deposit left. Australia 1200 years, China 79 years and Russia is 767 years. Now this calorific value of this coal again depends on the country from which this coal is sourced. For India, as I have already mentioned, the calorific value is low also for this coal, and this number of years this coal deposit is there, that will be lasting only 111 years. So anyhow we have to, this coal will be all exhausted after 100 years or so, and because of this greenhouse effect and what of this, yeah. So naturally for this purpose we have to go for this other like renewables or nuclear energy, so which will be actually for the energy source for our future. Now this is the uranium deposits as we have, as I am showing here. This is the Australia is amount in tons is 17 lakh tons, Kazakhstan 9,41,000 tons, South Africa 4,50,000 tons, Russia nearly 4 lakh tons, Canada 7 lakh tons, and India if you see only 1,29,000 tons. So India has 10 times lower than USA and 500 times lower than Australia these uranium deposits. So naturally we have to go for the other stages of nuclear energy program, like the second stage where we use the plutonium-239 from the in the fast breeder reactor, which is coming from the spent fuel of the first stage of the nuclear energy program, and also 233 uranium which is coming from the thorium-232 irradiated fuels. Now why thorium for India, which is a glimmer of hope? That is because that India is having one of the biggest deposits of thorium. You see the 9,80,000 tons of thorium in India compared to Brazil 6,32,000, Australia 5,95,000, USA 5,95,000, Egypt 3,80,000, China 3 lakhs and Russia 1,55,000. So thorium, we have got plenty of these thorium resources as compared to other countries, whereas the uranium deposits not only we have got less, we also have a poor quality ores. So because of that, of course now the things have changed after the 123 agreement. We are able to import uranium from other countries, but our vision from Dr. Homi Bhabha was based on this uranium deposit, which is very meager in India. Compared to that, whether we should have a thorium fueled reactors like thorium-232 converted to uranium-233, and then that can be used in the reactors as a fissile material. Now other considerations, now these are the good part I have said. Now what are the other considerations, like when you are talking about nuclear reactors, so there is going to be the waste problem, radioactive waste problem, which of course is one of the major concerns. So when the public, whether they are going to accept the nuclear energy program, so the major thing they are concerned about the radioactive waste, because whatever fission products are released after this nuclear fission, some of them are having very long half-lives, so they cannot decay over a matter of maybe few years or even few hundreds of years. So some of them will be active, still radioactive even after millions of years. So that is a major concern about the nuclear waste. But then there are strategies which are being developed in different countries and in India also, how to solve these problems, this radioactive waste management, whatever coming out of these nuclear reactors. So those long-lived radionuclides are actually separated and they are put in glass matrices and stored in deep geological repositories. So that is how these problems are solved. Also there are programs where you can have transmutation of these long-lived actinides as well as the fission products. Now you compare this, the waste which is coming out from coal. See, this coal is having this flue gas desulfurized, see this part, green, and also this ash including the norms. Now then you have this oil, see the waste, natural gas when it is burnt, this is coming this gas threatening, and this is the wood if it is burnt, and see the nuclear, so, and solar. So compared to this, you find that the nuclear is having very little waste. These are all presented here in million tons per gigawatt electrical yearly. You see the data, the whatever gases are coming out from the nuclear is very, very less. Now, worldwide average per capita dose from the natural and man-made radiation. You see the natural sources, when you talk about the radiation, radioactivity, so you get the radiation from this natural sources also, the cosmic rays, UV radiation you get. So these are worldwide annual per capita effective dose in millisieverts, and those are coming from this natural sources. Diagnosis, you go for X-ray, you get lot of dose from one X-ray when you do get it done, but that is because of the diagnostics. You know, like this COVID, this 19, there are many people who were affected, and when you go to the doctor asks about a CT scan. That is about 100 times more radiation exposure compared to one single X-ray. So now that is why people are exposed to X-rays, then atmospheric nuclear testing, from that also dose, but a nuclear power production, because it is everything is contained in a reactor, so the dose is very, very less coming for this. Now, relative environmental impact of different technology for the electricity generation. You see here I have plotted air pollution impacts, the picometer 10, and other impacts, and the greenhouse gas impacts. You see this is a low and this is high. So this is also high. So that means one which is in this part, that is best. So that means wind energy is best, and next is nuclear. So if you see the coal, so it is existing whatever coal technology, that is no gas cleaning and no coal, new coal technologies, natural gas technology, biomass technology, everywhere they are not as eco-friendly as compared to wind as well as nuclear. So nuclear is actually placed at a much better position compared to the other thermal energy production so this thing methods like your thermal power plants. Now this is, I am just giving a picture of this our Narora power plant and this is at I think this is a second stage, sorry not Narora, this is a second stage of nuclear power plant, NPP. It is a second stage of nuclear power plant, it is IGCAR Kalpakam. This is our first breeder reactor. And this is a PFBR which is coming up at Kalpakam. So this is a structure of this PFBR. Now with this, I have given a brief introduction of this nuclear power production. So I will summarize that we have three stages of nuclear energy. program. One is stage 1, which is in our advanced heavy water reactors fueled by natural uranium, which has 0.72% of uranium-235, is undergoing fission and producing nuclear energy. Stage 2 is the fast breeder reactor, which is coming up at our PFBR, as I have shown, which is a futuristic thing as envisioned by Dr. Bhabha. So there 239 plutonium is the fuel, and stage 3 is the 233 uranium fuel reactors. So these are all futuristic. And now, apart from these uranium-235 reactors, fueled reactors, there are also enriched uranium-235 reactors. Like in Tarapur plant, we had this enriched uranium, so we are importing this. In many countries, people are using this enriched uranium-235. So that is there for the stage 1 type of reactors. Now coming to the societal applications of the radioisotopes, this is the second part of this atomic energy program, which is for the masses. As you know that radiopharmaceuticals, there will be detailed lecture by Dr. Das, Tapas Das, but I just give a brief introduction here that the radiopharmaceuticals, which is a combined form of radioactive pharmaceuticals. That means this normal pharmaceutical what you are using, that does not contain any radioactive material, but the radioactive material is contained in the radiopharmaceuticals, are special class of radioisotope levels formulations suitable for administration in patients for either diagnosis or therapy. Diagnosis radiopharmaceutical, therapeutic radiopharmaceutical, there are two types of radiopharmaceutical. Most of the uses of this radiopharmaceutical are for the cancer treatment, but there are also some of the radiopharmaceutical which is not used for cancer treatment, but the general treatment also. Like you do know, for this cardiovascular disease, this technetium 99M spiked radiopharmaceuticals are used. Technetium MeB complex, they say that is used for this mapping of the heart functioning. So that is not for cancer treatment. Then this diagnostic radiopharmaceuticals, this provides the, as mentioned here, mostly with the PET scanning. I think most of you must be knowing about the PET scanning where the fluorine 18 is used. So this is the radio labeled molecules are designed for this, provide the images of intended specific organs or disease sites. So you have this X-ray, of course everybody is familiar about the X-ray radiography, where also you know this nuclear medicine, this gamma rays, is a gamma camera is there, and then you have the gamma camera detector, and of course you can find this imaging like this, where the radioactivity is there tagged in to the organs. So wherever it is tagged, you can get the switch off this.
We can switch off. Sir, come little front. We will take photo with all.
Yeah, okay. This is on, no? Yeah. Okay. So this is for the diagnostic radiopharmaceutical. Now there are also others are there, so therapeutic radiopharmaceuticals like this, where your radio labeled molecules are designed to deliver the therapeutic dose of ionizing radiations to the specific disease. So it can be mostly for the alpha therapy. Nowadays is alpha particle emitting radionuclides are there, which are used for therapeutic, but then this is slowly coming for application. But mostly you have this beta particles emitting, so that also does this therapy with an intention to cure the disease. Now this is how this radiopharmaceutical it works. So we have a radioactive radionuclide which is there, which is, of course I will mention how it is produced in the nuclear reactor. by neutron activation. I think some of you are carrying out studies on neutron activation. So some of this, once you irradiate a metal, that gets converted to a radioactive radionuclide. So that radionuclide is here. Now you cannot inject the free radionuclide into the body, because that may go to some of all the organs, and it may be also released much faster without doing the required job. So what is done is that it is formed a complex. It is stacked to a particular complexing agent, so that it is not directly in coming to the body as such. So it is inside the case of this complexing agent, and then this complexing agent, which is also passed to a this is something called a biomolecule is there. So that is how it will be going to the receptor. So we have this is the receptor in the body, which is the organ is there. So you have this biomolecule which is there, and there is a linker between this radiopharmaceutical complex, and there is a linker. So this is complexing agent is in the radiopharmaceutical term, it is called as the chelator. So we have a radionuclide, we have a chelator, we have a biomolecule, and we also have a linker, and then finally we have the receptor which is there in the body in the form of tumor, antigen cells, etc. So we have these biomolecules, we can have a peptide, we can have an antibody, we can have other biomolecular hormones, and for the diagnostic we have the technetium-99m, fluorine-18, this is for the PET scanning, gallium-88, this, and again this also is a beta plus emitting radionuclide, 64 copper, 123 iodine, 111 indium. So all these things are used as the radionuclide for the diagnostic. For the therapeutic, we have this iodine 131, 153 samarium, 177 lutetium, 160 holmium, 90 yttrium, and 188 rhenium. So these are the, you can see these are the normal cells, and these are the cancerous cells, and once this radionuclide, radiopharmaceutical is tagged to this receptor molecule, then this gives the dose, the required radiation dose to the cancerous cells and kills the cancerous cells, and that is how the patient is free from the cancer. Sorry? Mechanism. So mechanism is that, as I have already mentioned here, so this is the, whatever is existing inside the body. You form a complex with the chelator, and you have this biomolecule which is called the, which will go and form this, get attached to this receptor molecule. So then that means it is not getting distributed to other organs. So you have developed a radiopharmaceutical, let us say for liver. So it will go only to liver. It will not go to the other organs. Targeted radiotherapy. This is called targeted radiotherapy. Okay. So that will be detailed, will be explained by Dr. Das, Tapas Das. So that TRT, whatever targeted radiotherapy, that he will mention. Now in our BARC, we have this regular production and supply of medical isotopes. This 99 molybdenum, which is giving technetium-99 metastable with only 6 hours as the half-life. So there is molybdenum-99, that is called some cows are available, which is given to the hospitals, because technetium-99 metastable has a half-life, very short half-life of 6 hours. So you cannot use it, suppose produce at BARC and take to the hospital, it will decay in the road itself. So that 99 molybdenum cow, it is there, that is called a generator, technetium-99 M generator. So this generator is placed at the hospital site, and there this every day, whenever the requirement is there, technetium-99 metastable is eluted out of this generator, and it is injected to the patient. Similarly, iodine-125, this is again used, iodine-125 sources, seeds are made in our radiopharmaceutical division, BARC, and then they are sourced, sent to the patients in different hospitals. 131 iodine, again this is prepared in our radiopharmaceutical division, BARC, and through BRIT it is being given to different hospitals. BRIT is the Board of Radiation and Isotope Technology, that is a commercial wing of our Department of Atomic Energy, which sells this markets these radiopharmaceuticals. Similarly, 153 samarium, 177 lutetium. These are all again processed in radiopharmaceutical division, and yttrium-90. This also again is used for bone pain palliation, yttrium-90 based pharmaceutical. So these are the large scale productions. This production is taking place at radiopharmaceutical division, and also BRIT also is setting up some facilities where they are producing these radionuclides. You can see here, this is given a picture that these hot cells are there where people are working for this production of this, say particularly say iodine-131. So you have this master cell manipulators, the person is able to see there and then carry out this separation. This is for the iodine-131 setup, which is this glass, lab setup is there, and this neutron iridium tellurium oxide targets. Now iodine-125, as I have told, it is for used for this eye as well as prostate cancer. This iodine-125 seeds are actually made, and I think per patient maybe around 10 to 15 seeds are used for this eye cancer treatment. And this is a ultrasound image of the prostate gland implanted with iodine-125 seeds. You can see here. So they will be actually ultimately curing this or killing the cancer cells. Now this iodine-125, this has been a very old technology in BARC, particularly I think maybe for last 15 years or so this activity is going on. We are supplying. Now recently our Department of Atomic Energy also is providing for the patient ruthenium-106 for eye cancer treatment. Those plaques are also made and they are marketed by BRIT. Now this is yttrium-90 based radiopharmaceutical. This is the yttrium-90 hydroxyapatite HA for the treatment of chronic arthritis of large joints for the knee and hip. Now these are all, now you will say that why, now you are asking about the mechanism. So now this detailed how you go for which radionuclide, I think that Dr. Das will say. You will see basically the considerations are that what is the half-life of this radionuclide and what are the decay products which are going to be released in the body. And depending on the range of those, suppose there is a small tumor, then you can have a radionuclide, we can have a relatively small range. If it's a bigger tumor, for that the range has to be big. So these type of things, these decisions are there. And then of course now whether it is a prostate cancer, whether it is a liver cancer, so for that different type of, even for breast cancer also there are different type of radiopharmaceuticals are developed and those are being used. Now one thing is that I want to mention here that as you know that people are very scared when the people are very scared when somebody doctor says that you are having this cancer or that. So the first option doctor says that you go for the chemotherapy. So chemotherapy, if somebody is for the radiation therapy, people are scared that I have to use a radionuclide. So mostly the last stage patients come for the radiation radiopharmaceuticals. So that is the unfortunate thing. So the success rate, if you see, I think Dr. Das will mention, you can ask him, the success rate of survival of the patients by the radiopharmaceuticals that can increase manifold if the radiopharmaceutical injected at a first or second stage, but then doctors always prescribe that why to go for radiation, let us go for the chemotherapy. I think this perception is slowly changing. And new, more safe radiopharmaceuticals are being being available and coming to the market for the patients. And I think that is going to open up a big market for these radiopharmaceuticals. And this is again lutetium-177 HA for the treatment of chronic arthritis medium-sized joints. So this is a large joints. And this is for the medium-sized joints. This is like elbow, wrist, and ankle. Now these are some of the other radiopharmaceuticals like 64 copper, gallium-68. Gallium-68, it is mostly for the imaging because of this beta plus it is emitted here, so mostly it is used for this positron which is coming. So for that, from that it is the imaging purpose it is used, and also it is used for the therapy also. 90 yttrium mostly for therapy, technetium 99M, this is mostly for the diagnostic, and again for this 177 lutetium, 166 holmium, 188 rhenium, these are all used for different type of drugs. Now like here the DOTMP, this is the chelator which is used. So DOTMP, this is a macrocyclic complexing agent with carboxylic acid functionalities, and there are 3 carboxylates are there, and with forming a neutral complex with 177. Now again I will say something from the chemistry point of view. So wherever you have a 3 like a trivalent metal ion like lutetium, which is a +3 oxidation state, there you have the 3 carboxylates, so for that it forms a neutral complex. So if it is a negatively charged complex, then it will go to the liver. So that type of strategy is there, whether it will go to the liver or whether it will go to some other organs. And this TMP, so this goes to the particular treatment of this arthritis as well as this palliative treatment of painful skeletal metastasis. Now this is the PET imaging, because it's gallium 68 gives a positron from the beta plus decay. So there you find this PET CT images of this gallium 68 nota, this complex, and then this is the true positive scan for the TB spine infection range. So this, I don't know whether these pictures are very clear. You can see this by these radionuclides wherever are there, you find this light somewhat fluorescent type of images are shown here also. So wherever these radionuclides are there, so that gives the image. And also for this breast cancer patients who are treated with 177 lutetium DOTMP. So you see here this the arrows which show the preferential uptake of in the metastatic bone lesion sites. So you see here wherever this drug goes, so there the arrows are there. And then this 177 lutetium dotatate and gallium dota GA, and then these are some of these antibodies labeled radiopharmaceuticals. Lutetium 177 trastuzumab and lutetium 177 rituximab and pertuzumab. These are some of these antibody labeled radiopharmaceuticals are there, and they are also used for neuroendocrine cancer. Mostly these are used for the neuroendocrine cancers. Neuroendocrine means, I think it is for this your liver, pancreas and stomach cancers. For all those things it can be used. And these are the PET and SPECT images of the female patients suffering from the metastatic breast cancer. Again here this is all the fluorine 18 FDG and lutetium 177 lutetium trastuzumab respectively. These are the 2 things. This is a fluorine 18 image, and this is a fluorine 18. You can see the image is much more clear, and this lutetium is not that much, you don't get that much good contrast. So and I was mentioning about this ruthenium 106 seeds which are now BRC is giving to hospitals. So this is a ruthenium 106 plaque which has been made and successfully used for some eye cancer patients. Now this is in a summary, this production and supply of radioisotopes and radiopharmaceuticals. You have this target, which is the metal salt, and you have this encapsulation of target in this type of Harbel can. It goes for reactor irradiation. Transfer of this irradiated target, you have this some lot of shielding is required because now it is having radioactivity. So you get a lot of dose unless you put it in this heavy shields. And then it comes to this chemical processing of this irradiated target in the radiopharmaceutical division, where you have these hot cells. And finally, they make some formulation of these radiopharmaceuticals, again in the radiopharmaceutical division, goes to the hospital after this packing and marketing by Brit. Now these are some of the important radionuclei I have already mentioned, so I will skip this. You can see this technetium-99, this is a huge, lot of use is there for this. Again fluorine-18, these two are most popular. Gallium-68 is, is picking up. Now these are some of these isotopes which are used for diagnostic, mostly as I mentioned, technetium-99m and fluorine-18. And there are for therapy, there are other isotopes like iodine-131, iridium-192, lutetium-177, yttrium-90, holmium-166, iodine-125. These are all used. And then for pain management, like bone metastasis cases, you have rhenium-186, samarium-153, strontium-89, erbium-169, etc. And you see the demand actually, you get the maximum demand is there for technetium-99m as well as the fluorine-18. So, but demand is picking up. So, these are the major radiopharmaceuticals. Molybdenum technetium 99m generator, this is a workhorse of the nuclear medicine. Radio immunoassay brachytherapy, eye prostate cancer is iodine 125. Iodine 131 for treatment of thyroid disease. Samarium 153 for bone pain palliation. Lutetium 177 for the targeted therapy of cancer, bone pain palliation as well as radiation synovectomy. Bromine 82, these are all the industrial applications of some of this radiation, which I will be covering briefly. 82 bromine, which is used because it can be used in all three forms, physical forms like gas, solid as well as liquid. It is one of the very popular radioisotopes. It is used for the leak detection in industrial settings. Iridium 192 is for the gamma radiography. This is gamma ray radiography, this is used. You can see that again depends on the energy and also their half-lives. Iridium 192 is very popular because of this relatively longer half-life. Now coming to isotopes in industry, some applications I will just give here. This leak detection in buried pipeline and high pressure heat exchanger systems, flow rate measurement. Now this flow rate measurement, actually suppose you have some big columns where these liquids are flowing. So there you can always tag a radionuclide and see how the radionuclide is moving by having some detectors like the sodium iodide detector, gamma ray. I think some practical will be there. So you can see that how the sodium iodide detector is used, and there by putting this sodium iodide detector you can find out how this radionuclide is moving inside the pipes. So from that you can say whether it is a laminar flow or there is a turbulent flow can be found out. This has a lot of application in chemical industry, and also a lot of chemical engineering aspects can be found out by these calculations. And then residence time distribution, RTD measurements also can be done again by spiking a radionuclide and doing this gamma ray counting by sodium iodide detector. There are these softwares already developed and is being used by our colleagues in IRAD, that is Isotope Radiation Application Division. And then this radioactive particle tracking technique, this also is a very popular technique. This is used. Now this is a particular case I have shown here. This is in a Borosil glass factory, Gujarat. There is a problem in their quality control of this glass that they were getting. That is because of this non-homogeneous mixing of this, whatever this in the reactor. That you can see the reactor is a very big reactor from starting from here to the much end. It is maybe several meters, maybe 50 meters or so. So there a big reactor, that mixing of this glass chemicals in the liquid form or the molten form, the glass chemicals, that was not very uniform or not very homogeneous. So we have added a radioactive tracer there, and then we have carried out the measurements by radioactive counting, and we found out where is the non-homogeneity in the mixing. That has been rectified, and then the glass whatever was coming out after that, that has become very homogeneous and it passed all quality control tests. So this is one of the applications I have shown here for this isotope in industry. I think subsequently in some lectures it will be mentioned by Dr. Atanu. Then there is another one is isotopes in hydrology. You know, there is a lot of problem in our water resource management. There are many places where we have a drought, and also this water availability of water in some places is there only for several months, and for other months there is a water shortage is there. There are states like Rajasthan and Gujarat, even some parts of Andhra Pradesh also, I think there were water problems were there. So our colleagues from IRAD, that is Isotope Radiation Application Division, they have carried out extensive studies by doing isotope hydrogeology measurements. So what they do basically is this water is having the natural isotopes, that is hydrogen isotopes 1H and 2H, that is hydrogen and deuterium, and also oxygen. There are two isotopes, that is oxygen 16 and oxygen 18. So by monitoring the ratio of this deuterium to proton and also oxygen 18 to oxygen 16, they can find out actually the source of this water. So that, you know, by measuring this water isotopes, they can find out from where actually this is getting the recharge. You know, wherever the water sources are there, that will be recharging a river or a pond. So then accordingly this they can carry out the corrective measures so that this water in the river or the pond will be much more than whatever is there presently. So such studies has been very successfully demonstrated in Gujarat, Rajasthan and Andhra Pradesh, and also Uttarakhand. Uttarakhand, that the problem is that it is a hilly area. So when there is a rainfall in the rainy season, the water immediately it, you know, goes to the plains. So there is not much water is stored in the Uttarakhand, the hilly areas. So by carrying out this measurement of these isotopes, they can find out that what is the recharge point of this water in a particular lake. So then they build some, you know, storage tanks there, so that this water can last for several months. So whatever was there previously for maybe 1 or 2 months, now they are able to do it up to 6 to 7 months. This water can be stored there. So that is how this isotope hydrology has helped. Now this identification of this is a natural springs. This is for Uttarakhand. Then surface groundwater and aquifer interconnection. And also this estimation of residence time of groundwater. So sometimes you find that the groundwater residence time is depleting. So then if you know the recharge points, then that can be done by isotope hydrology. Then this residence time can be increased. Identification of source mechanism and pathways of the groundwater contamination. This is another one, I think in there are some requests particularly near Hyderabad, where this, I think, uranium contamination was detected in the water, and then this people were blaming our NFC facility that this is coming probably from NFC, this uranium, because that's handling large quantity of uranium. So there our colleagues from BRC, they have gone and carried out how this recharge in the groundwater is there, and they found out that this uranium is not from NFC, but it is coming from fertilizers. Sometimes, you know, the Punjab, you will see that there is a lot of uranium contamination in the groundwater. That is because of the fertilizer is used. So mostly uranium forms a very strong complex with phosphate. So most of these phosphatic fertilizers, you will find they are containing uranium. So when you use a phosphatic fertilizer, there will be some uranium in that. That is get concentrated in the groundwater. So that is the source of the contamination. Then this estimation of groundwater discharge in the coastal region and identify the origin of geothermal. This geothermal water, again, I think in our Badrinath, that our colleagues are carrying out some studies. That is a place called Taptakund. There I think that this temperature is around 50 degrees, so this, you know, hot water spring. Now they have observed that maybe some few tens of years ago it was more than 60 degrees. Now it has become 50 degrees. So they predict that it may become, you know, 40 degrees or 30 degrees. Then there is no effect of this hot spring. So our colleagues they have gone and carried out again isotope hydrology studies. They found out what are they are carrying out studies in collaboration with GSI, Geological Survey of India. They want to find out from where this actually is water source of this hot water springs. And then they can say that if there is some cold water spring also coming and, you know, trying to dilute this temperature so that those things can be arrested. So this is, I think, people are carrying out studies now. So this is how this our Uttarakhand, Uttarkasi. You see that this recharge structure constructed and the spring water at the Nakuri Ghat, Uttarkasi. See, this type of constructions are made such that this water can be there stored for a long time, and then that will be recharging the some of these springs. Now, application of radiation technology for food irradiation. This is one of the major applications. See this, and this is actually increasing. This food irradiation thing is increasing. Many times people are very much scared that the name of radiation. But if you see, go to the developed countries, most of this food, whichever is available in the market, so there will be a, like we have the vegetarian, non-vegetarian, some tag is there, no, that green dot or red dot or the brown dot is there. So there also you will find in the food packets, whether it is irradiated or it is non-irradiated, that will be there in the all developed countries you will find. So that is a very routine practice there, that food products are irradiated. Now this, you see here that this wastage of food I have listed here, that is 26% of dairy products, 42% of fruits and vegetables, 13% others and 19% grains. These are wasted worldwide. So how the wastage you can stop? That is because you can go for this irradiation. That is irradiation mostly carried out by the gamma irradiation. The source is cobalt-60, and then this is because these grains particularly you find that the insect will be destroying the food products, whether rice or pulses. You find that over the period of time it gets destroyed because of this insects infest this food products, food grains. So for that, there are other chemical methods. People used to put some chemicals, but then chemicals have a lot of harmful effect. You must have seen that they put some chemicals in the rice grains so that it will be lasting for longer period of time, because these insects cannot grow if the chemical is there. But then there that will be having harmful effect. So if you just irradiate these food grains, they can be stored for a longer period of time. Then this is phytosanitation to overcome the quarantine barrier in fruits and vegetables. This also can be done for fruits and vegetables. Inhibition of sprouting in tubers, bulbs and rhizomes. Delay in ripening and senescence of fruits. Enhancement in shelf life by destruction of spoilage microbes. So mostly for the fruits, vegetables and these dairy products, there will be this microbes, they will be spoiling. Then the elimination of pathogen. This can be eliminate these pathogens which are and parasites which are going to destroy the food products, that can be eliminated by applying the radiations. Now the benefits of irradiation is the radiation processing is a cold process, therefore unlike heat, it can be used on agricultural commodities without changing their fresh-like character. Radiation processing does not alter significantly the nutritional value, flavor, texture, the appearance of the food. Radiation processing improves the shelf life and hygienic quality of fish, meat and poultry. See, the fish, meat and poultry also are, they are highly perishable. But this irradiation has been done by gamma sources like cobalt-60 gamma. And also I think we have done by electron beam also, particularly because this frozen food, when you irradiate by gamma rays, the amount of time spent there is little longer because the gamma ray slow penetration. Whereas electron beam, if you use, then it's in a flash of time, this thing light, you get it irradiated, and so this there is not much lost. The temperature at the cold temperature itself you can do it. So that is how this is electron beam is probably emerging as a better technique for this fish, meat and poultry irradiation. Then radiation processing cobalt-60 cannot induce any radioactivity in food. This is what I think the common belief of people, that when you are irradiating, maybe that food product has become radioactive. That is the general belief. So I remember when when I joined BRC nearly 40 years ago. So that time there were this technique that food irradiation was taking place in the studies were carried out at the BRC. So they were irradiating this potatoes and onions, which are sprouting is there, and they were distributing that free batata vada, that is that potato stuffed vada, to anybody who wants to take, because it is irradiated. They want to test, and nobody was going to that counter because people were feeling that irradiated potato means that will be radioactive. So nobody was taking that. But I think after over the years, that concept has changed. Now that wherever that irradiated potato vada is there, so people take it there is without any problem. So radiation using cobalt-60 cannot induce any radioactivity in food and does not leave any harmful toxic radioactive residue on food, as is the case with chemical fumigants. This is a major problem if you use chemical fumigants. Due to the highly penetrating nature of the radiation energy, it is very effective method. Then pre-packed food can be treated for hygienization and improving shelf life. This is of course, actually one example is there that India was exporting mangoes to United States, and this Alfonso mangoes, and this lot of mango comes from Gujarat, that is the Kesar mango. So irradiated Kesar mango, if it is irradiated, that it can stay for months. So then I think our food technology division, BRC, they have carried out a campaign, and they have increased the export of Kesar mangoes to United States very, very significantly. And so that is one of the results actually when you do irradiation of this food. Then the radiation processing facilities are environment friendly, are safe to workers because there are a lot of shielding is there. So there is no problem so far as this. And there is a major hitch here, that is that knowledge should be there. If there is ignorance, then there is problem. There was an incident in Delhi IIT. So where sorry, not Delhi IIT, it is Delhi University, I think. Delhi University, there was there was a cobalt-60 gamma chamber was there. Some professor has taken and carried out research, and then it was a cobalt-60. Even though the half-life is, it should have decayed by that time, but then some amount of cobalt-60 was there, that is significant amount to cause damage. So the professor who has acquired that, procured that cobalt-60 source from DAE, he has retired. Then after that, nobody was using that cobalt-60. So then whoever the next HOD has come to Delhi University, he thought that what is this room is locked and there is a space problem. So let us throw this, what is this cobalt-60? So the professor has retired, so they have thrown it, they have given to that Kavadiwala. So that fellow has taken and sold for the metal recovery, and then few people died because of the whatever cobalt-60 was there. So after that our AERB, our Atomic Energy Regulatory Board, that is becoming very strict. Nowadays if you see, if you get a cobalt-60 source, you have to very strict procedure is there, and also you have to see who is the successor of this. So those of you want to set up a irradiation facility in your college or universities, so then you can always carry out this radiation processing or radiation based research, like solids you can take, irradiate and carry out other characterization and all. But then this problem should be taken care of, that it is safe provided it is shielded. The shielding is broken, then of course there will be damage. So this has to be taken care. If it is taken care, there is no problem. So how irradiation works? Irradiation works by disrupting the biological process that leads to decay, and in their interaction with water and other molecules that make up the food and living organisms. Radiation energy is absorbed by the molecules they contact, and the reaction with the DNA causes the death of the microorganisms and insects, and their impaired ability, the potato and veneer, to sprout. So this is mostly for this sprouting, whatever you must have seen, few weeks you buy potatoes from the market and you find that they are sprouting. So that can be prevented if you irradiate, if the potato is irradiated. Gamma rays. Yes. So this is one process and multiple uses. So sprouting innovation in onions, potatoes, ginger, garlic, etc. You can see the left side picture is a sprouted potato, and if you irradiate, this is a potato. And then quarantine the fruits, like I was talking about this mangoes. Insect disinfection in cereals, pulses, dry fruits. Then shelf life extension of chicken, meat and fish. pathogen reduction in spices and flesh foods. These spices nowadays, if it is irradiated, you get a label in the packaged product that this is irradiated spices. And this is the irradiation plant at Vasi, Navi Mumbai. So there are 26 irradiation plants are there in India, and the dose is, that depends on what you are irradiating. With very low dose, if it is onion and potato, only 0.1 kilogram. If it is a meat, you give a little bit of more. And if it is a medical product, that is for the sterilization, you have to give little more dose, that is 10 to 15 kilogram. So sterilization, we have a different facility, but then it can be there in the irradiation plants also. But in BRC, we have a isomade facility where the sterilization of medical facilities has been routinely carried out. So see, this is the unirradiated potato. You can see the sprouts, and these are irradiated potatoes. See, this is the strawberries, unirradiated and irradiated. This is the, you can see here after 60 days how these things are. They're stored at 4 to 6 degrees for 60 days. After 60 days, you find that they are fresh. They are fresh harvest, and after 60 days also, it is like this. Then this is non-irradiated food and irradiated food. It is, you see the onions, unirradiated, irradiated, another picture of this. And then control compared to the tomatoes. 1 kilogram after 10 days. You see, these things are rotten, but these are tomatoes are as good as fresh. Sir, what does it mean by kilogram? That is a unit of radiation. That will be taught, I think, in one of your courses. It will be there. So these are the spices, and then these are the development of fruit-based self-stable products deploying the radiation technology. These are all there available now. These are the jamun product. The self-life is now 6 months, then self-life 6 months for this strawberry product. These are all available. This BRC technology is available for this in our food technology division. They are all marketing these. This mango, banana, pineapple, papaya, apple, all these things are product made. This intermediate moisture fruit cubes are made, and then they are marketed. Now this global food irradiation market, see here by region, I have put it here, North America. See, North America is a very big market was there, Europe also is there, and then Asia Pacific, South America, and this Middle East Asia, I think. Then you see this, how these things are, demand is growing over the years. 2027, there is going to be much higher demand. But then I think this has been projected. These numbers only up to 24 data we have got, but these are all projected numbers. And these are some of the list of some of these food irradiation facilities which I have put it here. The isomate Brit is there. This is mostly for the medical equipment sterilization. This was set up in 1974, nearly 50 years ago. And there are, in a big way, this government of Maharashtra is actually taking up this food irradiation. There is a Lasalgaon where these onions are being irradiated. Huge amount of onions are irradiated. Now this revenue which is earned, this is a little old data, 21-22, by Brit, is a commercial unit of BRC, cell of isotopes. This is 135 CRs. This was proposed, but the actual was 175 CR. You can see that this thing, irradiation revenue which is coming out, this is much, much higher, and it is growing also, the demand is growing. Now another application of this radiation is the, you must have seen this, how the patients are exposed to this gamma rays. So then this is the Bhavatron developed by BRC, where the patient will be lying here, and then this gamma source will be, positioned where the organ is having cancerous cells, and then this gamma rays will come and fall, and they will be doing the damage to the cancerous cells, and that is how the patients are treated. This is also, I think, very popular technique, and many hospitals, I think, they are having these Bhavatron facilities. You can see here, now this gives a map of this, here how the patient is there, and this gamma rays are coming from this Bhavatron facility. This different hospitals in different cities marked here. So you can see in Andhra, you find this Nizamabad and this Nizamabad in Telangana now, right? So then Andhra you have got Vizag and Nellore also. So that there are different facilities. I think this is much more private hospitals also may be having some. They have shown some government hospitals, but then there may be a lot of private hospitals. They are also going for this. Now radiation sterilization of the medical products, as I have already mentioned, this is the isotope facility which was set up in 1974. ISOMED facility, which is there in India's first radiation sterilization facility. This is just outside the BRC campus, south gate of BRC, and there is a conveyor belt type of facilities there, on which this goes through around the gamma source and then it gets irradiated. There is a shielding is there, and these are the medical accessories which are all getting sterilized there. See, these are the shielding is there, and now this goes through this conveyor belt. These packets are irradiated, and person collects these packets and they are removed from this belt. Now this radiation also used for this sludge hygienization. This I think there will be in a special lecture it will be covered, but just I briefly mentioned that there are some, we have a facility, SRI facility we are having at Baroda. This is BRC facility where this R&D activity has started, and then this technology was transferred to the Ahmedabad Municipal Corporation, where they were having this sewage sludge, whatever is coming. Sludge means mostly the waste which is coming, and it has got mostly the pathogens, so that has to be killed. And then after this irradiation by the gamma rays, so then it can be used actually for plantation purpose. So there, because this nitrogen, phosphorus and potassium, this this can be spiked, this hygienized sludge, whatever we get, we can spike with this nitrogen, phosphorus and potassium, which are good nutrients for the plants, and then it can be used for this plantation. This process sludge is pathogen free and organic carbon rich manure, useful for soil health improvement, and this technology has been transferred to different municipal corporations, and we are also acting to in a very big way to transfer this technology to other municipal corporations. This Ahmedabad and Indore plants, they have been already, commissioning has been done, but then there are new plants coming up at Pune and Surat and many more municipal corporations. So these are the processed sludge bags, and we call these things as bio gold actually, this processed sewage sludge is called as a bio gold, and then they can be used for this plantation purpose. Now there is another activity which will be again actually in another lecture it will be highlighted, that is the dye wastewater treatment. This is again a application of this radiation technology where radiation can be used. You know, there's polymers, those who work on polymers, you know that polymer can be have initiation can be done by some radiation. Free radicals need to be there, whether you do by UV or you can do by also radiation. So then by allowing to this gamma rays to fall, then you can have this radiation grafted polymers can be made. So here we have this radiation grafted cartridges has been made, where we have taken cloth and we put a monomer and do the polymerization done there, which will be going for this anionic dye. Mostly it have done for the anionic dyes, and then this is the column which is used. This has been developed at Radiation Technology Development Division, RTDD BARC, and this dye wastewater comes through a pump, it goes to this, passes through this column, and then you get a clean water. And this has been demonstrated at Jodhpur, where we have set up a demonstration facility, and we have demonstrated at 75,000 liters per day scale. It has been done, and the technology is being transferred, and I think Jodhpur, there are 6 plants are coming up, where this cotton dyeing industries, they are taking up this technology, buying this technology from BRC, and their pollution control, state pollution control board also has approved this particular technology, and this is going to be used in Jodhpur, Rajasthan. I think again there are interest from Gujarat, where this will be Gujarat, Baroda, there is interest. So this technology will be used for the remediation of the dye wastewater. So whatever colored water comes, passes through this cartridge, you get clean water, means you can see the transparent water, there is no color here. And then whatever color is there, that is all captured in this cloth, and that can be used also subsequently. So this is the actual photograph of this dye wastewater treatment plant. Is set up at I think Sancheti and Co, some industry is there in Jodhpur. So there it is demonstrated. So finally, I will conclude that this peaceful uses of atomic energy, this is going to increase manifold in the coming years. Thanks to this setting up of new power plants, so our whatever energy we are getting from the nuclear plants, that is going to be doubled in a very shortly. And then of course there are applications like radiopharmaceutical, it's a very, very attractive option, food irradiation. Then nuclear agriculture, this part I have not, I've skipped here. I think there may be a lecture here where this mutation of this crops can be done by applying this gamma rays radiation. So there you can have a better variety of crop. I don't know whether there is any lecture in this particular thing. So that is another very good application. I think around 63 variety of mutated seeds has been developed at BARC, and compared to I think 200 odd by ICER. ICER is the Indian Council of Agriculture Research. So they are working in sync with BARC, and this 63 new varieties of crops have been developed at BARC. So those are all high yield. So the agriculture, when this cost of this production, they are significantly brought down. And then sterilization I mentioned, where these medical equipments are sterilized, and sludge hygienization, dye wastewater treatment, and many more applications. So thank you for your attention. I'll be happy to take some questions if anybody has.
So we can take one or two questions due to time constraint.
Sir, what are the physical and chemical changes when we irradiate any matter like vegetables or anything? Is there any physical?
Then store, we can store for a longer, that preservation is better. Anything, like tomatoes I have shown, they get perished. Tomato photograph I have shown once.
This may be because of the killing of the bacteria and all other things.
Yes. Yeah.
But I am asking about the physical changes and chemical changes inside the
Chemical change I have told is microbes, mostly those who are destroying, those things are destroyed.
Okay.
So that is how they are only perishing this material.
Okay, sir.
Now what do you mean by physical changes? I didn't get
Physical means any structural changes or morphological like
No,
okay.
mostly the bacteria,
Okay.
those are killed.
Okay.
Sir, in that sense, irradiated food is good, sir, for human.
That is what as I have shown that the demand is increasing as a function of years, and
Yes,
all developed countries like United States, European Union, they are all using. And in Asia Pacific also, that countries like Korea, Japan, they are also using. India is catching up slowly.
No, sir, within acquiring within a day or 2 days, the food is available in natural. In that sense, is it that
You
radiation?
don't say that you want to irradiate and immediately eat. No, it is all packaged. No, see, these
yes.
are you cannot go with 1 kg of potato and irradiate it. It is done in a big way. See, like Lasangaon,
Yeah.
they are having lakhs of tons of onions are irradiated.
Yes, sir.
Lakhs of tons.
So for
So they will
packaging
be-
and for storaging.
They will be packaged now
Yeah.
because they were under pressure.
Okay.
Suppose you produce, let us say, onions.
Yes, sir.
Suppose that sprouting starts after, let us say, hypothetically, I am telling, let us say 2 months.
Okay.
Now you are in a hurry to market it, in a month or so, such that it goes to reaches the persons those who are buying.
Yes, sir.
Now if it is irradiated, then it may be delayed for say several months.
Yeah.
So then you are not under pressure. So the farmers are benefiting.
Benefiting.
See, the other option was you go for the cold storage. Cold storage, you know, if you put it, that
cold
problem is there, that taste becomes slightly different.
Yes.
Potatoes, it becomes little sweet, you know, that cold storage potato.
Sir, so as compared to cold storage, irradiation is,
Yes, yes, irradiation is definitely, because that was the only option available before.
yeah, cold
To
storage.
farmers, cold storage for
yeah.
the potato and onions.
Yes, sir.
Now you have this option where it will be much lower cost wise, because you know very less amount of radiation,
Yeah.
less than 1 kilogram is used. So
Yes,
the
sir.
radiation, so immediately it will come out and then can be done.
Yes, sir. Another, sir, one of my finding, is there, sir, this new isotopes in nuclear medicine, particularly in diagnosis or therapeutic, this half-life of the,
That will be a detailed lecture on that. That is a factor consideration. That it should be that, you know.
no, then what is the relation between the deficiency of the, that what is medicine or something and the half-life?
No. This is decided based on the half-life. Suppose the half-life is less.
Yes, sir.
Let us select technetium 99 metastable.
Okay,
Technetium 99M.
yeah,
Half-life is only 6 years.
okay,
Now you inject to a patient.
yeah,
So after a day or so, the patient is not having any radioactivity in the body. Now you inject something which is a half-life of, let us say, 30 days.
yeah,
So the patient, wherever he will going, there will be some alarm. You know, that radiation detector, suppose you take to the patient, then there will be alarm. That fellow is having radioactivity.
radioactivity.
So naturally, half-life is a consideration. Similarly, fluorine 18 is having very short half-life. So the patient is injected, scanning is done, patient comes out, half-life radioactivity.
So half-life
It is an important consideration.
consideration. Thank you, sir.
And for therapy also, you have to see that how long it has to be giving the dose. So accordingly, that is decided. Several days maybe for that case. Yes, any other question or it's okay? Okay, I thank you.
So, if you have any doubts, you can interact during lunchtime also with Dr. Mahapatra Garu. Thank you. Now feedback by Dr. Suresh Garu.
So, good afternoon, one and all. Overall, the lecture on peaceful uses of atomic energy was informative, engaging and thought-provoking. The speaker enthusiasm and expertise in the subject matter were evident throughout the presentation. The speaker encouraged the audience to think critically about the benefits and challenges of using atomic energy for peaceful applications. I once again thank the speaker for delivering a good lecture. Thank you, one and all.
Now I invite our chief guest, Dr. Mahapatra Garu. We have small field station, sir, please. All faculty members of Department of Physics, please come onto the dais. Let us felicitate our chief guest, Dr. Mahapatra Garu. రామాంజలి కదా నెక్స్ట్ సవిసచ్ ఉంది అక్కడ ఉంది. Okay, now we'll have our session 2 on theory of radioactive decay, part 1 by Dr. Sabyasachi Patra. Now I request Srimati B. Durga Lakshmi garu to introduce Sabyasachi Patra garu.
Good afternoon, everyone. Once again, warm welcome to first day of this 5-day national workshop. I am delighted to introduce our next speaker, Dr. Sabyasachi Patra garu, a scientific officer F at Baba Atomic Research Center, BARC, Mumbai, and also working as an assistant professor at Homi Bhabha National Institute. He is a leading expert in the critical field of nuclear material assay for safeguard and security. That means he is at forefront of ensuring peaceful use of nuclear technology. Sir, contributions to this field have been widely recognized. He was awarded the prestigious Department of Atomic Energy DAE Young Scientist Award 2020, which is a testament to his innovative research and dedication. Also, he was a recipient of Mercury Action's Seal of Excellence Award in 2018. INSA PS Bilateral Exchange Award he received in 2017. Sir, we are fortunate to have Dr. S. Patra garu with us today. He will be sharing his insights on mainly theory of radioactive decay. Today and tomorrow first session also, and day after tomorrow also we have another session on radiation detection and measurements. Following his talk, I encourage you all to actively participate in question and answer session. Please join me in welcome Dr. Patra sir. Thank you, sir.
Okay, thank you, madam, for the nice introduction. So, welcome to this after the keynote address by our Honorable President NCAS. You have got the glimpses of the entire spectrum of DI activities, but now we will switch off into kind of more detailed technical lectures. So, please do not hesitate to stop me at any time. And as I was going through the list of participants, it is quite interesting that we have a very large diverse background. I could see some, of course majority is physicist, but I could see some participants from backgrounds like chemistry, zoology, even botany, and also some engineer, and that gave me a feeling that the nuclear science is truly getting a multi-dimensional subject, like truly interdisciplinary, so that we all actually have a common meeting point. So, first I place my apology if some of my slides look too fundamental, because I know that here we have many probably nuclear physics professors, for them it may appear very fundamental, but as we are targeting to deliver these lectures particularly for the students who are coming from the other background, so maybe my talk may look little more fundamental. And I set some learning objectives here. So, by the end of this lecture, we should be able to have a fundamental understanding of what radioactivity is. Of course, a little bit of history I will be talking of, and what is artificial radioactivity, natural radioactivity, decay types, half-life, decay and growth and equilibrium. And tomorrow we will switch to even more fundamental aspects of the structure of atom and what are the genesis of different kind of radioactive decay and all. So, let us see, I hope we all have a feeling like what is radioactivity that we all study in around school level, that we know that all the nuclei, they are not stable for some reason that will be coming later. So, they undergo spontaneous disintegration as a function of time, and this phenomena is basically named as radioactivity, and this as a result emit different kind of radiation, and you all know these names, like we call them alpha radiation, beta radiation, gamma radiation and so on. And this decay of the nucleus occurs due to its inherent thermodynamic instability, because as you know by law of nature, everyone wants to achieve a lower energy configuration, a lower energy state. So, atoms are also not an exception. Now, if we look back a little bit of history, that the chronology of the discovery of radioactivity, we must first start with this wonderful discovery by this William Röntgen. He is a German engineer. So, around this 1895, you know, just after the when there was too many work was going on this cathode rays. So, while he was doing some experiments on cathode rays, he observed some surprising, you know, unwanted new kind of radiation. What he observed was, although this cathode ray tube was enclosed in a black cardboard box, where you do not expect any light radiation to come out of this box, but accidentally there was some fluorescent screen, it was left in his lab, that was even in an angle where directly cathode ray cannot actually reach. He started seeing some glow in that fluorescent screen, and that is the genesis of the discovery of the X-ray. Now, the rest is history. As you know how useful today the X-ray is, like it can actually, you know, this is the first radiograph of the wife of Sir Röntgen, where he actually found that if you place your hand in between the source and the detector, you can actually image the bones inside. So, immediately this became a very, very useful tool for the medical physics, for the medical science, and the first Nobel Prize was awarded to William Röntgen in 1901. But just after the Röntgen discovery, as it happened today also, like something new come in a paper, so all the other researchers jump into it. So, there were majorly the groups by Becquerel and independently by this Pierre Curie and Marie Curie in France. They also, like all other scientists, they were trying to discover if similar rays are also emitted by fluorescent bodies under the action of light, because the fluorescence of this uranium and its compound were quite some time being studied those days. So, they again started relooking into it, and what was observed that, okay, they just put the uranium crystal in some photographic plates covered, they shine light on it, okay, and they found that the photographic plate darkened. So, they thought, okay, my hypothesis is working, like there must be some relation between the incident light with the observed phenomena, that is what we are nowadays calling as radioactivity. But so initially this was the understanding, but immediately when they succeed this experiment, the next experiment is always a control experiment. So, they just switched off the light, and they were expecting that I will not detect any more radiation in the photographic plate, but they were disgusted because it is still darkened, the photographic plate. So, then the confusion started, that the understanding that was made that the light is irresponsible, it is not true, but it is something which works even at the dark condition, which works even when you sealed the you know, that sample, and also the blackening is proportional to the amount of uranium. The more you take the material, the more it get darkened, and it also independent of the physical and chemical state of the uranium, whether you take solid, you take liquid, whatever form you take, it shows the similar kind of phenomena. So, this is they named as a phenomena called radioactivity. So, they say that there must be some sort of radiation which is coming out spontaneously, which does not need any trigger, and then subsequent discovery, if we look at, subsequent discovery if we look at, after that this Marie and Pierre Curie discovered this polonium and radium while studying the mineral pitch blende, and this polonium radium, polonium was named after the Marie Curie's homeland Poland, and radium was identified as even more radioactive element than polonium. So, these kind of studies they started doing. Around 1899 this Rutherford identifies this alpha and beta particles by this magnetic field experiment, and then subsequently around 1900 Wheeler discovered the gamma rays. So, this is the chronology. So, by which this radioactivity is discovered as a spontaneous disintegration of unstable nuclei by emission of radiation or particles, and for which this Nobel Prize was in physics was awarded in 1903 to Becquerel, Pierre Curie and Marie Curie. Now, just after this radiation was discovered, and this radium and particularly this Curie couple discovered the radium and polonium, there was some sort of craziness, like today also, like something is very interesting, so people will get crazy, and there was some fascination in the beginning. The fascination was something like, as you can see some of the photograph I just put here from available in Curie museum in Paris. Here you can see this radium was put in cigarettes, the radium was put in Thoradia, this is a very famous French cosmetic company. So, they used to put radium everywhere like in cosmetics. They used to use radiated water, as you can see some of the news, and immediately it was understood that this is not something which actually you can use it without any control. I must mention, like after the discovery of Roentgen also, people got crazy. They started taking, like discovery of camera, they started taking the photograph of their entire skeleton as a fun. So, they immediately understood the danger of this harmful effect of this radiation, as these radium girls, they were kind of dancer, they used to put radium on their clothes to glow. So, they just suffered radiation sickness, bone decay and leukemia. So, here comes the importance of the regulation and awareness of using radiation, as sir was also mentioning, like you have to be aware. Radiation is of course harmful things, but it can be extremely safe provided you have a good regulation and good awareness. Okay? So, that is why today radiation is used across wide fields including the medicine, industry, energy, scientific research, and is absolutely safe when used within regulated environment. That is what I want to convey. Now, switch to little bit of more technical part. After this discoveries of the natural radioactivity, here is of course another discovery, that is called artificial radioactivity. So, artificial means it is not naturally available, but you can induce radioactivity in any kind of nuclei. So, for example, you can see that if you bombard this iodine 127 with neutron, it get converted into iodine 128. So, and so. So, the first observation of this kind of artificial radioactivity was, in fact, you can see that even the first observation of a nuclear reaction by this Rutherford, who bombarded this nitrogen 14 to alpha and got converted to oxygen 17. So, this artificial radioactivity was first observed by Irene Curie and Frederick Joliot, who is again their husband wife couple, that is the next generation of Madame Marie Curie, and different projectile and targets, large number of reactions product were produced. So, this husband and wife couple were awarded Nobel Prize in 1935 for this discovery of artificial radioactivity, and first nuclear reaction with charged particle and then artificial disintegration of nuclei using cyclotron has been started, and a new branch in physics has been started. And then around 1938, here another groundbreaking discovery by this Otto Hahn and Strassmann, who discovered the nuclear fission by bombarding uranium with neutrons. And what was observed, that fission occurs when uranium atom split into smaller atom and it release enormous amount of energy. What sir was also talking, that it has so much potential that 1 kg of uranium actually can gives you energy equivalent to 25 metric tons of coal. So, you can imagine the enormous energy that is released by fission, and based on that the scientific and global impact was huge, and it forms the foundation of the atomic age, which transformed the entire physics of this energy production. So, the legacy is very rich, that is sparked, the discovery of fission sparked further research in nuclear physics, and of course led to the Manhattan project, which we anyway sir also taught that we don't want that, but that was the major scientific project that happened those days just after the discovery of the fission. But at the same time also we have the positive side that we could now get nuclear reactors which would actually enhance our energy need. So now you see that three kind of radiation, that is alpha, beta and gamma, they have different effect towards electric field, and the deflection is like alpha get deflected to negatively pole, so which indicates that it is having some positive charge. Small deflection, so there it must be some heavy particle. Beta deflected to positive poles, it must be having negative charge, and large deflection, so it is lighter particle. And gamma does not deflect, so it is electromagnetic radiation and does not carry any charge. And radioactive decay is a spontaneous process, energy is released. So this mass of the parent nuclide must be larger than the mass of the daughter nuclide. So the decaying nuclide we term as parent nuclei. So we will be frequently using these terms like parent, daughter. So the nuclei which is undergoing the disintegration, that is our parent nuclei, and the nuclei that is formed after this disintegration, this is the daughter nuclei. So as you can see, the penetration power of the radiation, you will be seeing in practicals also that we will demonstrate you some beta source, we will demonstrate you some gamma source. So you will be seeing that the penetration of this alpha source actually we could not bring because this has even stricter regulation to carry, but this alpha source is, the range is so short that it can be stopped by even a thin piece of paper. So just you put a thin piece of paper in front of alpha source, it does not proceed further. Beta can actually penetrate through the piece of paper, but it can be stopped by around 2 mm of aluminum sheet. But the gamma ray have a much longer range. Of course, it will, the range, actual range will depend on the energy, but typically around 15 to 20 centimeter of lead is needed to stop the high energy gamma rays. And if you look at their fundamental natures, like alpha is nothing but the nucleus of our helium atom, so it is helium plus 2. So the mass in atomic mass unit is around 4.0028. For beta, it is either negatively charged, which we call electron, or the positively charged, which we call positron, and for them the mass is much lighter compared to the alpha, and gamma does not carry this mass. And the velocity, if you compare with the light velocity, the gamma is basically the velocity of the light that you all know. So in comparison to this, you can now see the range of the alpha velocity and the beta velocity, that is much smaller. And the ionizing power for alpha is very high, beta is intermediate, and gamma is low. And what happens? Let us look that when something is undergoing alpha decay, it will move the Z, that is the atomic number, by 2 unit and the mass number by 4 unit. And you can see, for example, that uranium-235, if it emits an alpha particle, it will move to thorium-231, and this is called the half life. I will be coming just in a while that what is half life and all. For beta decay also, as you can see, the Z will be moving by 1 unit and the mass will not move to any unit. For beta plus decay also you can see, I will come in the subsequent slide, you will have a better understanding, and in electron capture also like this. So in gamma de-excitation, you do not move in Z or A, I mean the atomic number and mass number, and you just decrease in the energy, like from an excited state to you reach a ground state. I do not know if it is legible or not, but this is something like, when we first study chemistry or physics in our school, we get introduced into the periodic table of elements, that we call the most organized chart for different kind of elements. Similarly, for nuclear chemist or nuclear physicist, we have another kind of such organized table that we call the nucleate chart. It started prepared in a city called Karlsruhe in Germany. So they actually around 1950 they started preparing this chart, and this chart contains more than 3000 isotopes, like periodic table, more than 3000 isotopes, and they are organized based on their decay properties, their like this. So you can see this is a unique tool for the nuclear science community that presents structured and accurate information on the radioactive decay of nuclides. So it provides us these informations, like it gives me immediately, when I look at the chart, I can see the half-lives and the decay modes and the energies of the emitted radiation. So this is a very useful tool for nuclear physicist or chemist. And in contrast to the periodic table, a nucleate chart is based on the number of protons and neutrons in the nucleus of the atom. A nucleate chart is a two-dimensional representation of the nucleus, of the nuclear and radioactive properties of all known atoms. So, you can see that how a nucleate chart normally looks like. You can see in the vertical axis you have the number of protons, and in the horizontal axis you have the number of neutrons. So, you can see that initially this number of proton to neutron ratio, it is almost like 1, like in the initially. If you look at only this center line which is black in color, you will see that initially it is almost the ratio is 1, like equal number of protons and neutrons are present in the nucleus. But you can see after a while, in order to get the stability amongst this nucleus, the black line is the line of stability, they like whatever isotopes that is present in the black line, they are stable isotopes. You can see in order to get them, we have to deviate from this n by z is equal to 1, but we have to actually incline towards n by z more than 1. This is required because as you increase the proton numbers in the nucleus, the protons have Coulomb repulsion amongst each other, and this introduce some distability in the nucleus. So, you need more and more neutron to dilute the system, so that the proton-proton separation distance little bit increase in order to have a stable nucleus. So, you need more neutrons than protons as you keep on going to higher Z systems. And then you can see two other colors, that one is in this red zone, one is in this blue zone. So, this you will be seeing that if you are in this blue zone, that means you have, suppose if you are in this blue zone, let us say at a given system. So, you have more number of neutrons than what is required for stability. So, you have to actually undergo a radioactive decay in order to reach very close to this, either the black line or as close as possible to the black line. And similarly, if you are in the red zone, then also you have a tendency to reach as close as to the black line by means of radioactive decay. So, whatever nuclei which is present in this red zone or the blue zone, they are the radioactive, and by nature, by thermodynamics, they all wants to reach to these black lines. Okay. So, this is the genesis of radioactivity. Now, how to read these kind of tables? As you can see, we have different color codes for different mode of decay. As I say, the black is stable, this color is for the proton decay. I do not know if in this screen you can differentiate the color, but maybe in this screen you can refer, like for different decay modes you have different color coding, and by looking at this, when you have multiple color, that means your isotope has multiple decay modes, and depending upon the area share of each color in this particular box, it gives you the idea of what is the branching fraction of particular that mode in that particular mode of decay. So, while reading, you can actually see that when something is actually undergoing alpha decay, if you are here and you are kind of decaying through alpha, your position shift here. Similarly, if you are beta decay, your position shift that side. Similarly, if you are beta plus decay, your position like this and like that. Okay. So, I am not going into very detail, but if you are interested, you can actually refer to this wonderful literature, because it actually gives you a complete guidelines of how to read a nucleate chart, because it takes some time to grasp it, that how you can, but once you are used to with it, you will find it very handy to understand that what is going where. For example, if I take the example of this thorium-232 decay chain, you can see, if you look at the nucleate chart, you can see immediately after alpha decay it reaches to radium-228, after beta decay it reaches to actinium-228, further beta decay thorium-228, further alpha decay like this, and then finally you reach to the stable lead-208. Okay. Now, let us come that what is this, how the decay kinetics actually proceeds. So, as you can see that each nucleus of the same kind has same probability of decaying in a certain interval of time. Okay. So, I have n number of ensemble of unstable nuclei. For all of them, the decay probability is same. Be careful that I am using a term probability, I will just come some later that you will understand what is this importance of this term probability in radioactive decay. So, as you can see that this decay rate, if I want to write mathematically, that is nothing but minus of dn by dt, and that should be proportional to the n is nothing but the initial number of radioactive nuclei that I am present in my system. So, if I use some proportionality constant lambda, so this becomes, I can use the equal sign over here. So, minus dn dt is equal to lambda n, where lambda we define as the decay constant, and then if I just proceed further with this separation of variable, and then I solve the differential equation, you can easily end up to this kind of relation, where you will see that this n at any given time, the number of radionuclide present in a system, it is basically depending upon the number of initial unstable nuclei that I had in my system into e to the power minus of lambda t, where the t is the time elapsed since I started my measurement and lambda is my decay constant, right. So, you can see that the half life is basically, this half life is basically linked to this decay constant lambda inversely. I will just come, it is basically ln2 by lambda is your half life. What you can see is defined is the characteristic property of a radioisotope. So, for each radioisotope, this is its intrinsic property and is defined as the time needed for half of the given atoms to disintegrate. So, let us say I have 500 atoms, after one half life it gets 250, okay, like this, but I am again using a term probabilistically. So, I will just explain you. So, substituting this n is n0 by 2 when t is t half in the above equation, you get an expression for the t half which is 0.693 by lambda, and often number of atoms is not measured, but the radioactivity you are interested in. So, in that case the relation is activity, which is basically n into lambda. So, if you know the n and know the decay constant, you can actually convert the number into the radioactivity. Now, here I comes the very interesting analogy to explain you the radioactive decay, and as I was keep on telling you the term probability, 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 you will get a feeling like can we just understand the radioactive decay just like the popcorn in a hot pan. So, suppose you have a hot pan in the oven and you put some ready to cook popcorn on that. So, can you predict like after what time this particular corn will pop? You can't, right, because you can only say, well, if I wait for 2 minutes 50% of my corn will pop and 50% may remain unpopped. It is like this. So, it is just like a popcorn kernels pop at different times randomly, like you put a hot pan in oven, but different corn actually being popped at different time. So, similarly you have n number of atoms, 100 radionuclide atoms you have in a container. So, you cannot just say that okay, this atom will decay at this time. You can actually talk of a probability, like I have n number. So, after time t I will have n by 2 numbers in ensemble, but particular atom you cannot actually figure it out. And because while we cannot predict when an individual kernel will pop, we know that in a given time frame a fraction of the total will pop, similar to the half life of concept. And that is why in the definition of half life the probability is very important, like you cannot predict. For example, I say that you have 10 nuclei, after one half life how many will be remaining, you say 5. But if I say I have 1 nuclei, after 1 t half how many will remain, you cannot say half, no, because atoms you cannot have half. So, here it will be after another half life it will either decay or it will survive. So, in the analogy, let us look at, this is my time scale, and let us say this red dot is my my one unstable radionuclide in this instance. So, the question is, after time delta t, let us say I delay a time delta t. So, after this delta t, what is the probability that this fellow will decay? So, as you know the probability is lambda into delta t, because my lambda is the decay constant. So, if this lambda delta t is the probability of decay, then my story finished there. But if it survives, then what is the probability of survival the first delta t time interval? This is certainly 1 minus lambda delta t. So, let us say it survived and reached from that position to this. So, it changed its position. So, earlier it was here, now it changed its position from this to this, because it survived the time interval delta t. So, after it survived, then what is the probability that it will survive the second delta t as well? So, definitely it will be 1 minus delta t into 1 minus delta t. So, it will get squared. What is the probability that it will further survive the third delta t? It will be towards 3. So, if it has to survive nth event, nth such delta t interval, it has to be like 1 minus lambda t to the power n, something sort of, okay. And then I can see where n delta t is basically nothing but the total time that I waited during the measurement. So, mathematically you can actually convert that when this delta t tends to 0, like you have the time intervals very small. So, your n is number of such interval is actually infinite. So, as you know that this limit n tends to infinite 1 plus x by n kind of relation is, you can write as e to the power x. So, like in that form you can actually arrive at e to the power minus lambda t, that relation that we had in the last couple of slides back, that you have actually n is basically n0 into e to the power minus lambda t. So, you could actually understand now the statistical genesis of radioactivity and its probabilistic nature. Now, I am coming to the unit of radioactivity. As you know, this unit is either on the name of the scientist, of course, who discovered. So, it is either Curie or becquerel, and the relation is 1 becquerel means 1 disintegration per second, and 1 Curie is 3.7 into 10 to the power 10 disintegration per second. And there is another very interesting term that is called the specific activity, that is nothing but the radioactivity per unit mass of my sample, and that is, if you sorry, if you just convert, you arrive at a relation like Na into lambda by m, where m is the molar mass. Okay. So, for determination of the half life, activity of a freshly purified radioisotope sample is measured as a function of time. So, when plotted, an exponential curve is obtained, and the time corresponding to the half the original activity is your half life. So, you can see that the half life of the radioisotope can vary from a fraction of a second to actually several millions of years, depending upon the radioactivity and the mode. So, here I show you that, let us say I take the example of this 99M technetium, which is having a half life of 6 hours, and let us say you start from a radioactivity of 2000 becquerel or 2000 disintegration per second. So, with time, how actually its activity will fall, because we all know the relation we have seen that An is n0 into e to the power minus lambda t, or A is A0 into e to the power minus lambda t. So, you can see that if this is my A0, so you can see how the A is changing over time, right. So, if you just use a semi-log scale graph paper, I am not sure, I hope that many of you have particularly the students, like, did you ever use semi-log scale? Everyone? Then during the practical we do not need to explain, that is why I am asking, otherwise during the practical we will explain that what is the importance of semi-log scale. So, please feel free to let us know if you need to understand, but this is nothing but the normal graph paper that we have in millimeter scales. The one axis we convert them into the log scale, that is why we call semi-log. So, the x axis is still in the normal millimeter scale, and the y axis I converted into the log scale. So, the same graph when we replot, it gives me the linear kind of relationship, okay, because we had exponential relation in the linear, A is A0 e power minus lambda t, when you convert it in log scale. So, I can get ln A by A0 is minus lambda t, right. So, you get this kind of relation. So, from this kind of graph you can actually calculate that, okay, we initially had 2000 activity. So, after what time I have activity 1000, that is basically this. So, this becomes my first T-half, that is giving me around 6 hours. So, again this is giving me the second T-half, and so on and so forth. And of course, from the slope one can get the decay constant. Now, I am coming to the concept of branching decay. As you can see that, as I was showing you in the nucleate chart, that there may be 2 color in a given box. So, that indicates you there may be 2 different decay modes. So, you imagine that you have a bucket which is A, and you have only 1 holes in that bucket. So, the rate of loss of water from that bucket is only 1, but let us say you have like this. So, from the small hole it is liquid is flowing, and from the big hole also the liquid is flowing. So, for each hole, for each channel, you have different decay constants. So, you now I talk in terms of radioactivity, if you have 2 different decay modes, they may be having their independent decay constants, so lambda 1 and lambda 2. And it is basically, you can see that similarly if okay, and the summation of all the decay constant is basically called the total decay constant, or lambda, okay. For example, in the case of californium 252, it has 2 decay mode, one is spontaneous fission, one is alpha. We will come in tomorrow's class what is probably fission and alpha decay, but for now you just see that it is a 2 different decay modes, spontaneous fission and alpha. So, you can find out the effective half life, although the half life of the spontaneous fission and the half life of the alpha, they are very different, but you can find the effective half life, because effective half life is what we are interested in the measurement side, right. So, this effective half life is always the smaller than either of the individual half life. Now, I come to a situation, let us say you have 2 different radioactivity mixed together, okay. So, the A and B, they are mixed together, let us say you have this kind of situation, and where the decay constant of A is not equal to the decay constant of B. So, let us take a case where this decay constant of A is less than decay constant of B, let us say. So, if you measure the activity and try to plot in the semi-log scale, then this black line kind of curve you will be getting. So, how you can obtain the individual radioactivity? What you can do is, for example, from here if you draw a line, and then if you just subtract this red line from the black line, you can get the blue line. So, the red and blue actually give you the decay profile of the individual isotope, and which is supposed to be linear in semi-log scale, and you are getting so. So, the non-linearity in the total decay curve is because the mixing of these two radionuclide having two different decay constant, right. Now, in order to visualize, I just put some figures. I will just quickly explain you that how do you visualize it. For example, I am talking of a radioactive decay where the simplest case, the daughter nuclei that is being produced, that is stable. So, you have some unstable nuclei that is getting converted into the daughter nuclei. So, let us say for understanding, let us say I take 1000 balls of red color, they are radionuclides, 1000 nuclei of red colors, they are radionuclide, they are getting converted into stable, which is green in color. Okay. So, imagine when your time is 0, you have everything red. After it passes one half life, you can see roughly half of the ball turns from red to green. Then when they survived, when they again pass 2 T half time, you see the green component increases. After around 5 T half, you could barely see any red available, the majority is green. So, this is nothing but this profile, that this red curve if you see here, that you had 1000 unstable nuclei in the beginning, but after 5 T halves you have around a few hundreds of less than a few hundreds of nuclei available in your system. So, you reach to less than 10% of the system now remain radioactive. Similarly, you can look at the growth profile of this green. Okay. So, the growth profile of this green will also follow this kind of nature and will attain a saturation kind of thing. So, this is because of their mathematical form, that this Na is Na0 e to the power minus lambda a t, that we already talked so many times, and for the Nb it is nothing but the Na0 into 1 minus e to the power minus lambda t, that is why it is taking this mathematical form. And from this you can actually find the age of this particular radioactive atoms. Okay, that how many from a given time T0, what is the time that has been passed when I am measuring the radioactivity, that can be actually calculated. Now, coming to a little complicated scenario where your radioactive decay, but the daughter nucleus is also radioactive. So far we were talking about the case where the daughter was stable, but now imagine a case where the daughter is radioactive. So, then it is analogous to this kind of situation. So, let us say you have your parent which is basically decaying to some bucket. So, I am just analogously using it with as if you are pouring water from one pot into another pot. So, let us say when you are using this pot to pour water, this is the radioactive pot, let us say, but when you are putting in another bucket, if this bucket has no more holes, then it is the stable nuclide. But in this case I am saying the daughter is nuclide radioactive, this means this bucket has some hole, analogously I am talking. Okay, do not get confused with actual bucket and hole, but I am saying that there is some decay modes that is open in this system. So, there will be some loss of water from this also. Again it is pouring in another bucket which have a different size hole, again it is pouring. It will be keep on continuing unless we find a bucket which does not have any hole, that is our stable nucleus. So, in natural radioactive decay series you will be seeing that so many decay processes, then it suddenly stops at lead. Why? Because the lead is that kind of bucket which does not have that hole. Okay. So, until then it will keep on flowing like this. So, as you can see that A is being converted to B, B to C, C to D, D to E, and like that, and these half lives of the radio elements differ. So, it is really having some complex growth and decay curves and differ from system to system. Okay. So, if you look at mathematically, for sake of understanding I take only this kind of simple system, that A is being converted to B with a decay constant lambda A, and B is getting converted to C with another decay constant lambda B. So, how you can mathematically write? This is nothing but the rate of formation of this B is nothing but the rate of decay of A minus the rate of formation of B, right. And then if you just simplify it, you arrive at the expression for the number of B atoms at any given time t, that is basically lambda A by lambda B minus lambda A Na0 into e to the power minus lambda t minus e to the power minus lambda bt. And similarly you can convert it into activity also, and you can convert the decay constant in terms of half life also. That is simple mathematics that you can actually do. When it is further very complicated system, let us say chain of decay, you actually arrive at this kind of equation which is a very famous known as Bateman equation, where actually you can calculate the number of atoms of any given nth species which is available in the system as this kind of expression, where the C1, C2, C3, Cn are having these constant which are basically decay constant dependent. So, now I am coming to the case where the daughter is radioactive. We basically have three kind of situation. You can imagine, like either the parent nucleide is having less half life than the daughter, either the parent nucleotide is having comparable half life with the daughter, or either the parent half life is having more half life than the daughter. Let us talk of the first case. You can see that parent half life is less than the daughter. This means the parent bucket hole is bigger than the daughter bucket hole, is similar to that. So, you can see that the parent will decay, but the daughter will then slowly decay. When they are comparable, it is almost like comparable the rate at which it is falling, the same rate it is going. But when this kind of situation is appeared, the parent is longer lived than the daughter, that means parent is actually releasing the water very slowly with a very narrow hole, but whatever water is being consumed, it is now getting drained, because it does not no longer depend on how big this hole, because the supply itself is limited. So, even though this hole is bigger, but it cannot undergo a faster decay rate because of the limited supply, and this is a condition called radioactive equilibrium, which is achieved where the daughter is bound to follow the parent decay kinetics in spite of having its faster own decay mode. So, if you try to visualize in similar way this kind of situation, that when your tau p is less than tau d, you can see that the tau p is decaying fast and the tau d is decaying, and then after that when all the parents almost decayed, the daughter also decay. In the same kind of color convention, you can see the green is basically the intermediate one and the blue is basically the stable one. If I go to this kind of situation where these are comparable, you can see that the parent decays like this, the daughter grow and decay like this. So, the total cumulative profile you can see like this. Same plot if I do in log semi-log scale, you can see this kind of nature. Okay. But the most interesting one, which I will be discussing in more detail, that is the example of this tau p when it is greater than tau d, that is we are talking of radioactive equilibrium. So, where actually you have the cumulative decay profile, it looks like this, because the parent decays like this and the daughter grow like this, and after a certain time this daughter is bound to follow the radioactive decay of the parent, okay, decay kinetics of the parent, and that is a condition we define as radioactive equilibrium. And this equilibrium is basically named of two types depending upon the how the tau p is far or near from my observation time scale. Okay. So, when this tau p is when this tau p is kind of less than or almost in the comparable to the observation time scale, we call it transient equilibrium. Transient mean you all understand, it is a short time. But secular, when this observation epoch tau p is much greater than the observation epoch, like say natural radioactivity decay, it is being actually happened over a million of years, and I am observing only maybe for a few months, few years, whatever it is. So, that sense it is the secular equilibrium, and you can see the secular equilibrium arises when the parent's half life is about roughly 100 times longer than the half life of the daughter, then we define it as secular equilibrium. Okay, but there is no sharp boundary that what is transient, what is secular, the physics is same. And as you can see that the most useful example of secular equilibrium in natural radioactive decay, as you can see this uranium 238, uranium 235, thorium 232 decay, and as I just mentioned a few slides back that they all actually arrive at the stable isotope, that is black. So, I am almost near the end of my presentation, where I will be just giving you an example of a radioactive equilibrium. As sir has mentioned so many slides that he mentioned the importance of this radionuclide generator, right. So, I just took one example that you see you have molybdenum 99 which have a half life of around 66 hours, and let us say you have this technetium 99 which has technetium 99M which has a half life of only 6 hours. Now, we call this technetium 99M as a workhorse of nuclear medicine, because as sir mentioned that when you inject it in your body, within the day of experiment your radioactivity level in your body actually reduces. So, that is very important. You cannot put a radionuclide which will sustain in your body for a long time. Okay. So, but the problem is, let us say we are producing this technetium 99 in Bombay and you need it in Rajamundry hospital. So, the time we will arrive at Rajamundry, all my technetium 99M will decay. So, what we want is in the Rajamundry hospital we will just provide this molybdenum 99 itself in a radionuclide generator, which is a basically which will be discussed in more details in the radiopharmaceutical lecture. But you imagine that you have a molybdenum 99, okay, you have in some generator where this technetium 99 will be growing, technetium 99M will be growing, okay, and it will attain the equilibrium, because the half life of the parent is longer than the half life of the decay. So, the moment it reaches the equilibrium, technetium 99m will now follow the decay of the parent. So, you will be always having some equilibrium concentration of technetium 99m available in your system. So, whenever you actually need that, depending upon the demands, on site production can be made by just chemically elute the technetium 99m from your generator. So, this is called radionuclide generator, and that is why it is analogously compared with milking of a cow. Like we have cow in our home, whenever we need milk, we can just milk it out cow every morning. So, similarly, you just imagine that you have a molybdenum technetium 99 generator at your hospital. So, you just see that let us say they are in equilibrium. So, after one day, let us say every day morning your patients comes to your hospital. So, every morning you can actually elute, because the molybdenum 99m, it is following this decay curve, technetium 99m that is growing in this decay mode, but every morning if you just elute it out, your technetium 99m activity reach here. Again throughout the day it will keep on building up, again next morning you are eluting it out. Okay. Like that successively you can actually use a moly generator for molybdenum technetium 99 generator for a long period, let us say up to 7 days you can actually use, which is having a half life of only 6 hours. So, you can understand the importance of this radioactive equilibrium. So, mathematically it is basically that whatever we explained so far, that the activity of this technetium 99m will be following this kind of relation, and the time for the maximum activity, after how much time it will attain the equilibrium, that will depend on this Tmax, which is basically 1 by lambda 2 minus lambda 1 into ln lambda 2 by lambda 1. So, after every Tmax also you can actually get it eluted. Okay. So, this we are talking can be milked out. So, with this I will conclude my today's talk. So, we will continue tomorrow. Thank you so much, and if you have any questions, please.
If you have any questions, if no, then I request Sri Ram Garu for feedback.
Good afternoon, one and all. Present speaker, Sabjasi Patra Garu, clearly explained about the importance of radioactivity and artificial radioactivity, natural radioactivity, half-life, and decay and growth and applications in medicine also. And also he clearly explained the importance of nuclear chart as well as the applications in the medicine. So we hope it is clearly and also he is explained clearly, so the participants from other background students also can easily understand the concepts. So thank you, sir, thank you very much. So
now we will be having lunch, then after lunch all of you should gather here by 2:15 in the seminar hall. In the same hall we have to gather by 2:15. So, you can go for lunch now, and at 2:15 we will have the introduction to practicals and formation of groups, and after that we will go to the labs. And the attendance is mandatory for all the participants. Please do not leave after lunch. You may be feeling sleepy, but you should attend the practicals. So, all the participants I think provided with the food tokens. So, use the food tokens for the lunch. You are given